Okay. Okay, so we start the last day. We will tell about the tectonic of the Himalaya with a brief overview, with the main tectonic unit, with a focus on the metamorphic core. And then we'll speak about the main fault and shear zones, such as the main central thrust, so Tibetan detachment, and the higher Himalayan discontinuity, with the kinematics and timing. And we will apply some of the things that we learned the days before. Okay, so we started to see what is the general architecture of the Himalayan belt. The Himalaya is very famous, it's the most famous collisional belt in the world. Most people study it, and the Himalaya provides a good look to a continent-continent collision. It is the world's youngest and highest mountain range. There is the fastest uplift rate, up to 10 millimeters per year in the Nanga Parbat, in the northwestern part of the belt. There is the world's maximum relative relief. There is the world's largest high plateau, the Tibet, more or less 5,000 kilometers, and it is produced from almost an orthogonal collision between India and Asia. As a morphology, you know very well, the length is 2,500 kilometers, and we have the two corners of the indentation that are the Nanga Parbat on the northwest and the Nache Barwa to the northeast. And actually, the convergence rate by GPS is nearly 5 millimeters per year. And so you have active faults, as Mahesh showed very nice yesterday. You can see here a picture showing earthquakes and velocity of deformation by GPS. And this picture is from a book, Himalaya Dynamic of the Giant, edited by Epard and Catin, two French geologists. There are three books with this collection, and it is written especially for master and PhD students. I sent the PDF to Mahesh. There are several topics and could be useful for you to go into depth of the geology of this beautiful mountain range. Okay, just to recall the history, there is a fragmentation of Pangaea supercontinent. As you can see, India moved for maybe all over the world, from south to north, up to collide with the Asia continent. There is also a northern part that is now included in the belt, that is called Greater India, is one that is now no more present in the continent, but involved in the deformation of the belt. And during the subduction of the Chinese lithosphere, the rate of convergence was very fast, up to 16 centimeters per year. And an Andean type margin developed in the Lhasa block, characterized by trans-Himalayan calc-alkaline batholith with volcanites. And after collision, the rate of convergence decreases at more or less 4 or 5 centimeters per year, close to the collision time, maybe 60, 55 million years. It's just a look from an old picture from a French geologist, Allègre, that show more or less the development of the belt. You have also southern Tibet here, northern India here, and a lot of convergence, subduction, collision between southern Tibet and northern Tibet, the Mangong Nuyang Sushar. Then the subduction of the lithosphere below Tibet, magmatic arc, calc-alkaline arc, more or less in this part. Then collision, the development of a Indo-Sushar zone, and then the formation of the main thrust, such as the main central thrust, main boundary thrust, main frontal thrust. The age is not very well constrained because the paper is quite old, but just to have an idea what happened it is a nice scheme. Okay, Himalayan belt is also famous for the indentation tectonics developed by Paul Tapponier in the 70s. He made several analog experiments with plasticine and the wood, and he more or less was able to reproduce the main fault due to the movement of India to the north, indentating into Asia. So this is a picture. You can see the main fault, the extrusion of China to the east and South China to the southwest. And this was a picture of one of the first experiment made by Paul Saponier. This is one of the original picture of these experiments that linked to these experiments. And here, also in this picture from Himalaya dynamic of a giant, you can see the aerial photo of Tibet and Himalaya. And here by Taponier Molnar 1976, the slip line model with a prediction of the geometry of the strike slip fault. This is a model, more or less, a very simple model. And you can see the real strike slip fault linked to the indentation. It was a nice discovery, then also exported in another part of the world. So now we give a look to the geometry and architecture of the belt. Here you can see the main rocks, the main tectonic units. In red, you can see the Indo-Suchar zone. In dark red, the Ganges batholith, the Andean type arc during the subduction of the oceanic lithosphere. In yellow-orange, there is a Tethyan sedimentary sequence, the more or less a sedimentary sequence with very low or no grade of metamorphism, with the deformation top to the south with the folds, reverse the folds, and so on. In the middle part, you can see a lot of this red stuff that are north Himalayan granite or gneiss dome that has the same rocks as in the Greater Himalayan sequence, that is the violet color here. The yellow line is more or less the trace or the main trace of the South Tibetan detachment, separating the Tethyan rocks from the lower Greater Himalayan sequence. Here you can see close to the detachment, this red stuff are leucogranites, Miocene leucogranites just emplaced below or within the South Tibetan detachment here. Then in green, the lesser Himalayan sequence, and in green also the main central thrust with several window in this part, sun clip, the other part, then the main boundary thrust and main frontal thrust, and then your country just here. This is a nice picture from a Swiss geologist in the 90s, made a nice PhD thesis in Zanskar. And this a cross section, you can see the suture, the batholith of Ladakh, the Theta Himalayan sequence, and there is also here the Tsomorari Nap with eclogites intruded in the Puga gneisses, and the Nap crystalline is a Greater Himalayan sequence. With the Zangska shear zone is a strand of the South Tibetan detachment, with top down to the north normal sense of shear, associated with the intrusion of leucogranites. Then the main central thrust, the main boundary thrust, the less Himalaya here, with some antiformal shape in the frontal part of the belt. This is a picture built up by Max Searle at the altitude of Kathmandu, central Nepal. More or less the same things. There is no the Tsomorari Nap in this part of the belt. But what you can see, a large amount of leucogranites and granite seal just in the upper part of the Greater Himalayan sequence and close to the South Tibetan detachment. Some leucogranites are really deformed and sheared by the movement of the Greater Himalayan sequence. You can also observe some isograde of minerals, sillimanite, kyanite, sterolite. So approaching to the main central thrust, there is an inverse metamorphic gradient due to several factors, maybe deformation, sure. You can see also the external clip of the greater Marian sequence. Sometimes in this clip are some rocks of the Tethyan sediments. So more or less the same. You can see here also the Gorka earthquake rupture zone. The Gorka earthquake was caused by this step geometry of the main frontal thrust just below the belt, because in this part strain accumulated for 100 years and then was released during the 2015 earthquake. Okay, this is just another view of the same thing by Rick Lowe. You can see more or less also the topography here, and the units are exactly the same. This red line is more or less the brittle zone where earthquakes generates, because we are in the upper brittle part of the crust is brittle way of deformation. Below there is a creeping zone in pressure and temperature increase, so deformation is slow and continuous, so with no development of earthquakes. Okay, we start to give a look to the Theta Himalayan sequence or Tibetan sedimentary sequence, a different name of the same unit. You can see here, this is a road from uh, the road to Leh, from okay, from the I don't remember the name, Mana, from Mana to Leh. And during the road, you can see these beautiful folds. The sediments are really deformed in very large folds continuously. And so by this kind of fold, you can calculate the shortening that is has been estimated to 700, 1,000 kilometers. Just 150, 300 kilometers have been documented in the folded and trusted sediments of the Titan sedimentary sequence. This is a total shortening, sorry. And the minimum of 650 kilometers of shortening have been detected in the Lesser Himalaya. And whereas in the Greater Himalayan sequence, because you have a lot of metamorphic rocks, so the folds are much more complex. So there is metamorphism, superposed fold. It is not possible to calculate the shortening, but sure is higher than the shortening recorded in the upper Titan sediments and the lower less Himalayan sediments. Just a look to the rocks. Here you can see some Triassic limestone, some Ordovician limestone. This is a drill for paleomagnetic studies. These are in Appel, a German geologist working on paleomagnetism of the Himalayas. It's quite famous. And in this very simplified geological section, you can see the lower part of the Greater Himalayan sequence, the South Tibetan detachment, then the Tibetan rocks with limestone, and at the base of the limestone are strongly foliated and with a little bit metamorphism. Then you have orange limestone, limestone is shale at Devonian time, Silurian Devonian, Carboniferous and Permian sandstone and siltstone, but more or less what we can observe is usually an increase in deformation and in temperature approaching the Greater Marian sequence, because here you have leucogranite injection complex made by dikes and silts and migmatites. So you have very hot rocks below the Titan rocks, so there is a transfer of heat from below to the upper part. So this, at least the base for 800 meters, 1 kilometer, so the base is a little bit metamorphosed by dynamic metamorphism, because the heat transfer happened during the shearing of the South Tibetan detachment. And probably, since there are this kind of faults, very, very common, reported in the Tibetan Himalayan sequence like this. We are more or less close to Lhasa, the Lhasa or the road from Lhasa to Mount Everest in the Tibetan side. There are a lot of South Virgin Falls and thrust with up to the southwest and south shear. So probably the Tetian sequence was firstly trusted on the Greater Mayan sequence and then affected by shearing, normal shearing at the base. Sometimes people forgot this, especially in calculating the amount of displacement of South Tibetan detachment, because the superposition is not only due to the normal shearing, but first thrust and then shearing. So it's tricky. It's difficult to calculate the amount of displacement. Going down, we are in the higher Himalayan crystalline, that is a metamorphic core of the belt. Has been classically differentiated in three formations by Patrick Lefort in the 70s, but of course they are not formation because we are not in a sedimentary sequence, but there are at least a unit or complex. So the upper one, the unit 3, is just this one in this part, is made by orthognesis and migmatite gneisses. You can see here a picture in Western Nepal with large feldspar porphyroclast, and below a picture from Western Bhutan. You can see the white stuff are crystal of sillimanite, very huge crystal, and the red dots are garnets. So is a garnet and sillimanite bearing gneisses from the upper part. So we are just in this unit, the pink unit, below the Tetian rocks and above the main central thrust. Okay. So other picture from the Greater Mayan sequence. This is from Mount Makalu. You can see strongly sheared gneisses with very big garnet crystal, testifying by grade or medium grade metamorphism. It's a similar orthogneis to the previous picture. They are very common, and when dated, there are of Ordovician age, these orthogneises. Okay, the Greater Mayan sequence is made also by a lot of white marble, calc-silicate gneisses, with minor amount of pelitic and psamitic rocks. You can see here a boudin of calc-silicate in Western Bhutan, in Western Nepal, and here a thin section of a marble, where you can see the calcite crystal, obviously deformed with grain boundary migration or twins like this. So you can study the microstructure of this rock very easily. Going down in the unit 1, there are more or less kyanite and garnet bearing paragneiss and mica schist. You can see kyanite in the field here in Western Nepal, kyanite in Kaligandaki Valley, and the kyanite in thin section like this. This mineral is kyanite in quartz matrix. There are also some, of course, calcosilicate and boudin of garnet bearing amphibolites. It's basic composition. So we are at the base of the Greater Himalayan sequence, called also Higher Himalayan crystalline, but in the last few years, Greater Himalayan sequence is the most common used name. In this picture, you can see some other rocks, garnet, kyanite, sterolite, migmatite rocks at the mesoscale. At the microscale, you can see sterolite with internal foliation, garnet, sorry, sterolite here, kyanite, white mica, biotite, quartz, and here you can see a beautiful garnet with an internal foliation truncated by the external foliation. This is from the chapter of the book Himalaya Dynamic of a Giant, where me and colleague Centurion described the tectonic and metamorphic feature of the Greater Himalayan sequence, just an abstract but is useful. Of course, in the Great Himalayas sequence, in the upper part, there are a lot of migmatites. Mm, Maybe half part of the Great Himalayas sequence is made of melted rocks. You can see here melt this stuff, leucosome, concentrated along a shear band at the outcrop scale. And this sigma type porphyroclast in migmatite linked to the top to the south shearing. That is the main deformation affecting the metamorphic rocks in the sequence. Sometimes you can observe folds in the migmatites, and leucosome try to concentrate along the axial plane of the folds. Here you can see also some sheared leucogranite dike, because migmatite are associated with granite and leucogranite, and probably they are the origin of the leucogranite. And you can see the sigma type shape to the top to the southeast sense of shear. Oh, this is an old picture from Nialam in southern Tibet, just at the boundary between Nepal and Tibet. This is gneiss with some dikes of leucogranite. This a piece of leucogranite intruded in these high-grade rocks. And this is a tourmaline bearing leucogranite in Gangotri, in India. There are, of course, a lot of granite in the upper part. It's just an aerial a picture from the flight from Kathmandu to Bhutan. This is Mount Everest, Mount Lotz. Here you can see this white stuff is a big intrusion of granite. The thickness is 4 or 5 kilometers. Here you can see a big leucogranite seal in Bhagirati. Is more or less Tethyan rocks, Great Himalayan sequence, and in between there is a big seal. This is the horizontal attitude of this seal. Okay, this is Bhagirati Massif, our camp some years ago, and a lot of rocks and a lot of moraines, more or less. So it is a picture of the Mount Makalu. The Mount Makalu is made at the top by leucogranites. You can see the dark stuff below. There are migmatites, and if you give a close look, you can see that there are a lot of dike and seal from the migmatite, and they increase in volume towards the upper part until they build up the main granite of the Makalu massive mountain. Okay, this kind of leucogranite are highly differentiated granite with paraluminous composition, sometimes with garnet, white mica, and so on. But they are now considered for the formation of lithium and rare earth element because of the rapid crystallization and shearing. So the shearing is very important to generate lithium-rich pegmatites. This is a picture from this very recent paper, just published a few days ago. Here, Rambuk Monastery, the Mount Everest, Chomolagma is the Chinese name, and these red stuff are all the granites. This Choyo Mountain with Pusila granite. So there is a road here coming from Tibet to Nepal. So it is quite easy to reach this kind of granite. This no, this is much higher. But there are a lot of granite with possible interest for rare earth elements and lithium that is now very important for energy transition. Okay, there is a nice intrusion in Western Nepal that we found several years ago. This is a granite never found before that we named the Buraburi. That is a double peak, means sister and brother, more or less, Nepalese, if I remember well. The very important feature of this granite that is included both the Great Himalayan sequence in pink and Tibetan sedimentary rocks in light brown. So it is one of the few granites including the South Tibetan detachment. As you can see in this picture, the granite is isotropic, has no deformation, so you can put a limit on the deformation of the activity of South Tibetan detachment. This is a picture showing the granite in the lower part, this kind of rocks. These other rocks are sedimentary rocks of the Titan Himalayan sequence. This is a pass that we are not able to cross because on the other side there was a lot of ice, so we come back. So we made several expeditions from southern part, from northern part, just to map the granite, and at the end we mapped by aerial photos and um, other kind uh, of similar things because of course there is no coverage of vegetation because we are more or less at 5,000 meters of altitude, so the rocks are very well exposed, so it was very easy to map. The area of this granite is 110 kilometers square, and the thickness is more or less 5 kilometers from the base to the top. And it was never mapped or before our expedition because it is a very far region, not used by tourists. So paradise for geologists, more or less. Okay, just a few pictures from the Lesser Himalayan sequence. So if you go down from the Greater Himalayan sequence, we found the Lesser Himalayan sequence, ripple marks here in Western Nepal, and some cross bedding in quartzite in this picture. Okay, just an overview of this tectonic unit. If we give a look to the metamorphism of Lesser Himalaya, main central thrust zone, Greater Himalayan sequence, people detected a difference in the PT path because in Greater Himalayan sequence there is a PT path like this, pressure and temperature, increasing pressure and temperature, peak, then exhumation, decreasing temperature, decreasing pressure more or less at the same temperature, then decreasing both during the final stages of exhumation. Greater Himalayan sequence reach pressure of maybe 1.6, 1.8 gigapascal. The main central thrust zone, the boundary between the upper main central thrust and the lower, show a PT path like this, more or less. So a little bit different with lower pressure with respect to the Greater Himalayan sequence. And the lesser Himalayan rocks, when involved in the belt, show the so-called hairpin PT path. So very different shape, this one. So they go quickly to pressure, but no high pressure, then come back to exhumation. Because lesser Himalayan sequence is more or less confined in the upper class. The pressure are no higher than 5 kilobars. And you can see here more or less the provenance of this PT path. The blue came from this Greater Himalayan sequence, the yellow-orange from the main central thrust zone, and the green from the lesser Himalayan sequence in this way. Okay, now we'll give a look to the main fault and shear zone. This is South Tibetan detachment, the high Himalayan discontinuity, and the main central thrust. In this picture from a paper of Garzanti 2019, we can see a section of the Greater Himalayan sequence. Here, the South Tibetan detachment at the top of the metamorphic sequence. In the middle part, the high Himalayan thrust or higher Himalayan discontinuity, the main central thrust zone, the main boundary thrust, and so on. Here you can see in this schematic cross-section, South Tibetan detachment, the high Himalayan discontinuity, main central thrust, and this is an out-of-sequence thrust, this red line with dotted red line. Okay, there are more or less also the ages of this shear zone, 25 up to 11 million years South Tibetan detachment, high Germanic discontinuity between 27, 28 and 16, 17 million years, main central thrust less than 16 million years, then main boundary thrust younger than 10 million years. You can see also that in this picture, the upper Greater Himalaya is found also in the North Himalayan gneiss dome. There's a Titan sediments here and here. In the middle part, you can find this alignment, east-west alignment of gneiss dome, North Himalayan gneiss dome, and they are made exactly by the same rocks and the same leucogranites that we found in the frontal part of the belt. One of the main feature of this uh, shear zone is spectacular continuity all along the belt, because the same feature you can observe in Bhutan, Nepal, India, in several sections, more or less they have the same characteristics. So it's very uncommon because, for example, if you study the Alps, the tectonic boundary are different characteristics. It is not so linear, the orogen, and is much more complex. In this way, at least from this point of view, we are facilitated because of this beautiful continuity of the shear zone. Okay. For the STDS, the direction of tectonic movement is towards the northeast, and the displacement is about 100 kilometers calculated along the Mount Everest section. And the blue line marks the South Tibetan detachment. The lower thrust fault, the main central thrust, has a top to the southwest contractional sense of shear, so it is like thrust, of course. The displacement is more than 200 kilometers. Okay, if you give a look to the arrow, you you have more or less in the Greater sequence an arrow. Oh, sorry, this an arrow like this, an arrow like this. If they sum up, they make show a big arrow pointing to the extrusion, a movement to the upper part and to the south of the Greater Himalayan sequence. Uh, in this way, is a STDS MCT. The movement is like this, of course, is a normal sense of shear. So if you sum up this vector, you have a big one with the south-southwest. So means that these kind of rocks in the greater Himalayan sequence are extruded, are pushed towards the south by the kinematic of this fault, because you move this part down and this part up. So just as a consequence of the kinematic of this two bounding fault shear zone, there is a movement to the upper part. Here uh, we are in the Kaligandaki Valley, this Mount Dhaulagiri, that is now 8,000. And from the footpath to Annapurna Base Camp, there is a place where there is a nice view where you can see more or less the trace of the main central truss and the trace of the Annapurna detachment here, that is a strand of the South Tibetan detachment. And all this stuff is the Greater Himalayan sequence. Mm. Is, of course, a panoramic view, a little bit contracted. In these mountains, the Lesser Himalayan sequence, and you can see here this part. This part is made by the foliation deep into the north and some fracture deep into the south, and they made a big collapse of slope coming down and building up hills up to 500, 600 meters of altitude in the Kaligandaki Valley. There may be this one, the big one. So uh, it- also this kind of foliation sitting deep into the north. So at least at the first sight it could be stable, but if cut by joints or faults deep into the south, they can cause a wedge failure of the rock. And this is one of the biggest I've been seen in my life. So, okay, in this section are from George Gruitz and Isabel Cotan from the Himalayan Dynamic of a Giant, showing more or less two cross section, one from Bhutan, more or less. Yeah, you can see main central thrust a little bit folded down, the South Tibetan detachment, the Kangmar Dome here, or organized dome, and here a section from Mount Everest, where we can see made by old paper, one of my first paper in the Himalayas, 1998, and Serle 2003, where we can see Mount Everest here is Tibet. The Mount Everest is cross-cut by Chomolungma detachment, that is a brittle fault with the top to the top down to the north sense of shear, and the Lhotse detachment here below. This is a ductile shear zone. This is a brittle shear zone. So in this, in several parts of the belt, the South Tibetan detachment is not only made by one shear zone, but we have a lower ductile shear zone and an upper brittle shear zone. But in not every place it is the same. Then there are some normal fault like this, high angle normal fault cross-cutting the detachment. And in this way, you can see this brown stuff that is a Norcol formation, so-called Norcol formation made by low-grade metamorphic rocks or up to medium grade that show a thickness of a few thousand meters here. But since this fault merged to the north we can observe these low-grade non-metamorphosed metamorphic rocks that occupies the top of Mount Everest directly on top of the high-grade metamorphic rocks. I will show you some picture later. Okay, now we give a detailed look to the main central thrust. The main central thrust is this line in between orange and green the unit with some tectonic window and some clip. So, okay. There is a problem of definition of the main central thrust because it is one of the main tectonic feature of the Himalayan belt, but there are several definitions, so it is a mess when you can go to see the map, and people put the main central thrust in very different ways. So classically, main central thrust have been defined as a boundary between higher Himalayan crystalline or greater Himalayan sequence and the lower, lesser Himalayan sequence. This was a definition by Haim and Ganser, 1939, and therefore located at the lithological contact and partly metamorphic variation. Other authors, such as the French colleagues, especially some years ago, Lefort, Colchen, put the main central thrust at the kyanite in isograde. When kyanite started to grow in the rocks, they put the main central thrust. So it is interpreted as essentially as a metamorphic boundary. Some authors point to the occurrence of a zone of high-grade Eiger deformation, such as Searle and others 2018. There is a nice paper on Geological Society of London, just a review paper with some suggestions. I suggest you to give a look to this paper. So they say if it is a shared zone, it should be characterized by high strain. This is, of course, it is correct. The main problem is that sometimes the formation is heterogeneously distributed. So you have sometimes you find several zones of high deformation. So it is not really easy also to follow this very clear uh, criteria. More or less, the main central truss, it is not a single truss surface, but there are at least two main surfaces, an upper main central truss, a lower main central truss that Arita, um, Japanese colleagues, called the main CT1 and main MCT2, uh, or it is an extensive zone of deformation that we call the main central truss zone, because if you go from the higher truss to the lower truss, you found maybe kilometers of mylonites with no solution of continuity. This is a summary of the criteria used to define the main central truss. The first one is the structural criteria. So you have high-grade ignesis and migmatites in the upper part with a ductile shear zone in between the upper and the lower unit. In the below, you have low-grade metasediments, the lesser Himalayan sequence. The main interpretation is major thrust, so up to the southwest movement, and shear zone with mylonite. So very high strain shear zone. This could be the most classical definition, the most useful. There is also metamorphic criteria. You have amphibolite facies metamorphism with silmanite rocks above, a green schist facies to the south below. So there is a metamorphic discontinuity with inverted, sorry, there is an error here, inverted metamorphic sequence. There is a lithological criteria, aragnite, migmatite, and leucogranite above, phyllite, quartzite, and carbonate rocks below. So there is a lithological contrast. There is also a geochemical criteria, epsilon neodymium, because if you give a look to the rocks from the great element sequence or from the lesser element sequence, epsilon neodymium point to younger sources in the great element sequence. So this value is from 15 to 10, and epsilon neodymium in below the main central truss in the lesser Himalayan sequence point to 25 to 20, pointing to the very much more older source from the Indian Creton. So there is also an isotopic boundary. Some people use also detrital zircons to gain the age of sedimentation of the rocks. And also in this case, you have concentration of ages from 1.2 to 0.5 gigahertz, a little bit young with respect to the lesser Himalayan sequence below. It is 2.1, 1.8 gigahertz, much more older. So it is based by different sediments provenance. It is more or less confirmed by several authors. But the main problem is that, for example, in central Nepal, the main central truss has been put by Max Serre, for example, in the lesser Himalayan sequence, maybe 30 kilometers away from the main central truss marked by French geologists, so in the lesser Himalayan sequence, when the formation disappear. And some people, for example, put the main central truss up to the migmatite in the upper part of Greater Himalayan sequence. In Bhutan, in Sikkim, Himalaya, there are map with the main central truss in the migmatites. So there is a very strong difference in distance and the kind of rocks involved um, in this problem. So sometimes it is not easy to compare map from different part of the belt. There are some picture for the main central truss zone. The picture are from George Gruitz, for the most part, apart the two insin section from Salvatore Iaccarino and Chiara Montomoli. Here you can see a sharp contact in the picture A, SC fabric or SC prime fabric here in fill lights is a very common aspect of the main central thrust in the field. Also, you can see here some orthognesis involved in the deformation. So in this case, you have uh, sigma type porphyroclast ORC structure. You can see uh, very penetrative foliation in this orthognesis, and usually when you are away from the main central thrust, the deformation is not so strong. So also the gradient of deformation suggests the occurrence of the shear zone and also kinematic indicators. Here you can see some SC fabric, not well observable in this picture. We stop to the south. There are some rotated garnet in the main central thrust zone. This picture from Salvatore Iaccarino from Turin, or some mica fish like this. This photo is by Chiara Montomoli, maybe from Western Nepal. So very large mica fish, suggesting a top to the southwest sense of shear. So about the sense of shear, there are no problem, both at the mesoscale and at the micro scale. This is a picture of main central truss. We see fabric with a very large distance. This is a lens cap, and you can see the distance between C plane is maybe 20 centimeters, so very huge SC fabric, or some asymmetric boudin in quartzite like this. And usually the stretch inclination, we can see a little bit here, deformed, is northeast plunging, sorry, and the SC fabric are subhorizontal. You can see the pole here. Okay, we are in Uttarakhand or Garhwal, India, with some colleagues, Salvatore Carino, Chiara Montomoli, and Dario Visona. And we are in the main central thrust. This is a rock of the Greater Himalayan sequence. This is sheared rocks, and here the Lesser Himalayan sequence. Some beautiful kinematic indicators in fill lights with quartz deformed quartz vein. So you can see C plane and S fabric here. There's a dextral sense of shear. In these carbonate rocks, there are foliation fish. You remember that mica fish is only one crystal. These are aggregate of mica and chlorite, so they have the shape of mica fish, but since they're aggregate, we call the foliation fish. But anyway, the sense of shear is up to the southwest. Okay. The main central thrust is famous, has been known all over the world for the inverted metamorphic sequence. You can see some cross-section from Lefort that maybe was the first to recognize this feature in main central thrust. This more or less in the Maca. No, okay, anyway, Eastern Nepal. You can see chlorite, biotite, garnet, staurolite. This Marziandi River. Kyanite, sillimanite. So going upward, you can observe an increase in the occurrence of metamorphic minerals, increasing the metamorphism. So there are several models envisaged for the explanation of this inverted metamorphic sequence. The first one was the hot iron, because you have the Great Himalayan sequence with gneisses, migmatites put above lesser Himalayan rocks, very cold. So there is a transfer of heat from above to below, and this causes the growth of metamorphic minerals with decreasing temperature downward. Another explanation is localized simple shear. Hubbard, 1989, GIAN and Manikaswagam, 1993. So you can have okay. Another explanation is the folding of the isogrades. Um, Localized simple shear. Okay, we can. There are picture about after. Okay, these are more or less the three main mechanism of explanation. Another one is the channel flow, because you in this picture, mainly from Mike Searle, Rick Lowe, Laurent Godin, you have molten rocks here. They are moving to the south. Now at the surface of the belt, in the frontal part, cropping out rocks that were molten 20 million years. But with this movement, you have a hot channel with molten rocks that moving upward. So in the upper part, in the South Tibetan detachment, you have a deformation, a high strain zone. So the you have more or less a normal metamorphic sequence with the telescoped isogrades. You have sillimanite, kyanite, sterolite, garnet that approaching the shear zone are sheared and they become closer and closer each other. In the lower part, the same isograde underwent a passive deformation. So they are sheared, but you have here the sillimanite, the kyanite, sterolite, garnet. So it is not like a folding, but it is just a propagation of the heat in the frontal part with a normal sequence here, inverted here, and then sheared along the main central thrust. Because just it is the shear that make the isograde to go very close. Okay, this is more or less the model of a simple shear. You have a normal metamorphic sequence with the thrust movement and the main central thrust and a lot of simple shear. You cause the inversion of these isogrades, more or less. In this picture that I drew few months ago, you can see a non-deformed rocks below. Then with a large amount of simple shear, with a very large gamma value, you can rotate the lines strongly to the right. So if you put some lines, maybe 200 degrees, 300, 400, 500, 600, with a certain distance, after an angle of deformation of 25 degrees, these lines are rotated to the right, so the red distance in between the lines become shortened. With an angle of deformation of 42 degrees, the line are rotated to the right more, and this distance is decreased a lot, maybe 5 times with respect to the initial one. So in this way, by simple shear, you can explain the telescoping of this ogre that you can observe along the main central thrust as an inverted sequence, and along the South Tibetan detachment as a normal one. But this happen everywhere when we have shear. Also in the Est-Variscan shear zone, if you remember, I show you that close to the Est-Variscan shear zone, we have the same increase of metamorphic Barrovian minerals. This is in the Est-Variscan shear zone. It is not due to thrust or normal fault, but to strike slip to transpressional deformation. In transpression, the telescoping is much higher because we have also a component of compression perpendicular to the boundary. So this line are flattened and put close to the other. It's very common. Okay, about the age of the main central thrust, the age there are several ages with different methods, with different rocks. The main problem is what are you dating? Because if you put the main central thrust in the migmatites or in the lesser Himalaya, you are dating different things. So it is not easy to gain the ages. In this paper of several years ago, we compared the ages of the higher Himalayan sequence with respect to the main central thrust. The main central thrust, more or less 1713, 2510, 2513, 25:8, 16:9, 19:15. So more or less the range of age is this one. In the paper by Godin and others, 2006, and a special publication of Geological Society of London, published in 2006, a very, very nice volume. They put ages in between 25 and 16 million years. But probably not all these ages are related to the main central thrust. These are probably little bit accurate. Okay, for example, to gain good information about the age of movement, there is also this paper by Catherine Mottram in Sikkim. They used yttrium maps for garnet and monazite growing during the formation. Sorry. So this is a nice paper because it shows very well how to use garnet and monazite and at the same time with chemical mapping. So you can uh, refer to the prograde metamorphism and retrograde metamorphism happened during the main central thrust activity, and they use the yttrium content of monazite and garnet because when yttrium is sequestrated by garnet, it is depleted in the contemporaneous monazite, and the opposite happens when yttrium is released by garnet during retrometamorphism, and it is sequestrated by monazite. So monazite during the retrograde metamorphism show high yttrium rims in the crystals, like the ones that we observed in Argentera Massif and so on. Anyway, they found ages in between 17, 12 million years, and probably some deformation post 10 million years. So it was very accurate way to calculate the deformation using both microstructure, tectonics, geochemistry, and geochronology. I will show you some details of this method when we will deal about the higher Malayan discontinuity. Okay. So we worked a little bit in Uttarakhand. So we collected sample from Laknanda and other valley, and of the main central trust. And during the PhD thesis of Chiara Montemagni, published in 2018, 19, and 20 in several papers. So the last one is in Terranova, about the main central trust. We detected the mica growth along shearing, some static mica above the mica growth along the formation. So we gained the ages of the main central thrust, of the Vaikrita thrust and the Munziari thrust. We are able to date the upper and the lower portion of the thrust. Here more or less the Munziari thrust here, the Vaikrita thrust here, the way to Gangotri. Here is a section with the Munziari thrust, the lower one, the Vaikrita thrust, and the Greater Himalayan sequence up to the South Tibetan detachment here, the so-called Martoli fault. Some sample were taken also in the Alaknanda and Dauliganga valleys. The Dauliganga valleys were able to reach the South Tibetan detachment close to Malari, because in Malari there is a granite that is interpreted as include both the Greater Himalayan sequence and the Tetian rocks. Some people published it is undeformed, but in reality we were here with Arvind Jain from Roorkee University and Pulak Mukherjee from Dehradun, I think. And we found that the granite is sheared, so it is not undeformed. There are some undeformed dike, but the granite is completely sheared. Anyway, we took several samples to date the South Tibetan detachment and the main central thrust here, with close to Tapoban, here close to Joshimat, and okay, the other part I showed you before. So this is a section Laknanda Dauliganga valleys, and we had these ages. Sin clearing mica 8.2 million years, and post S2 mica 7.4 million years. The static mica, this one, the static crystal growth after the formation for the Velkita Trust. The Munziari were more or less close to 5 million years. More or less the same ages in the Velkita Trust, Laknanda and Dauliganga, 9 million years. The formation stopped by static micas at 6 million years. And the Munziari Trust, more or less 5.35 million years. This was a very nice work by Igor Villa and Chiara Montemagni on argon-argon geochronology. And so we can say there is also in this picture from the paper 2020 on Terranova, we were able to also make some vorticity analysis to detect the amount of pull shear, simple shear, but not with classical method, but examine with X-ray the whole sample without cutting, but just showing the images. The name is oh, I now forgot, but I will come back later on this. Anyway, the Vakrita Trust was active in between 9 and 10 million years with a vorticity in between 0.75 and 0.95, point to the dominant simple shear deformation together with less amount of pure shear. After that, we had the growth of static mica along more or less at 7 million years. This means that you have the shearing at 9, 10 million years, then shearing stop. You have the growth of static mica at 7 million years, so no more deformation along this part. Then deformation migrated southward, downward to the Munzari Trust that was more or less active at 5 million years. So the upper and the lower thrust or shear zone of the main central thrust zone are not active contemporaneously, but this is older and the lower, the Munzari thrust, is younger. And at the time of activation of the Munzari thrust, deformation was characterized already by non-coaxial deformation, but with a dominant pure shear. And we can explain this because you are adding a lot of rocks to the Munzari Trust, so the lithostatic load increases, and so increases the amount of pure shear in the lower part. So younger and with a lot of load. Ah, I don't remember the name of the method. Um, vabbè, okay. Okay. Can we make minutes of stop? Have you some question about this? The window, MCT. Mm. Uh, you mean to the poles? Yeah. Oh, because mm, after the formation of MCT, you have the development of duplexes in the lesser Himalaya, and you have accumulation of duplexes, and you can make some antiformal fold. So you have some antiform and synform, and depending of the erosion, you have some clip and some window. especially in eastern Nepal. Gosa-Inkund, wind of, or some similar names. I think it is they are due to the deformation in the Lesser Himalaya that passively deformed the main central thrust. Okay. Okay. Kick off the tea. Within 10 minutes, we come back. South Tibetan detachment system. There is a problem for the flat attitude of the South Tibetan detachment, the problem of low angle normal fault. Then I will give some information about the geoheritage sites of International Union of Geological Science, then the architecture and kinematics of the detachment, some microstructure analysis, and an overview of the geochronology. So, as you know, in the Anderson model, normal fault, you have the main stresses, the sigma 1, the main stress is vertical, sigma 3 and sigma 2, the less and the intermediate stress axis are horizontal, and usually you can form a normal fault with a high, mm, uh, high angle attitude. So usually they should be inclined at nearly 60 degrees. This is a classical angle for normal fault, close to the surface of the earth. But as so in experiments, you can broke some sample. You put sigma 1 here, and the two conjugate fracture made making an acute angle. So this angle should be more or less 30 degrees. So the dipping of the normal fault is usually around 6 degrees and so on. Because, as you can see from this picture of a confossen, when you move a surface with respect to the force or to the stress, the from horizontal, you move this surface in this way. The maximum shear stress, you can see the stress and the angle of surface as a maximum shear stress in this position at 45 degrees with respect to the stress. But of course, the rock is made by uh, is not just pure material with no chemical composition. You have a friction, you have a cohesion. So usually this in nature, this angle is lesser than 45, and this is close to 30 degrees, right? Because you have also the competition in between the normal stress and the normal force, because at 45 degrees, the normal stress that is perpendicular to the phase is still very high, so cannot allow a good slip along the surface. Okay, and when we deal with a low angle normal fault, we means mm, that we have a fault dipping 10 degrees or 20 degrees. So in a very flat attitude. With a very flat attitude, you are in situation like this, where shear stress is too low and normal stress is too high. So it is for from a mechanical point of view, it is almost impossible to have a slip along a low angle normal fault. Low angle normal fault are, of course, very common in metamorphic core complexes. You have myelinite like this, folded in antiformal way with brittle fault above. So it is a big problem. Uh, so some people think about that normal low angle normal fault there were high angle normal fault then rotated. It is a good explanation, but it is not good for the South Tibetan detachment because it is quite flat, but it is flat all along the belt for more than 2,000 kilometers. So we cannot imagine a rotation of all the belt from steep altitude to flat altitude. So we can face the problem with other thinking to something different. Maybe some strain softening mechanism that allow the deformation to go along the surface, a flat surface. You can use fluids. You can allow the occurrence of leucogranites that are melted along the South Tibetan detachment, so they can allow the formation very easily, a mechanism of strain softening, or it was before a flat thrust, and then reutilized as a normal fault. This is also another possibility to explain this strange attitude of the South Tibetan detachment. Here you can see a picture from the South Tibetan detachment. You can see leucogranite completely deformed, sheared along the detachment. You can see very well C plane, S plane in this leucogranite to the top, to the north, since the South Tibetan detachment system in the Rombuk Valley, in the north slope of Mount Everest, has been included in the first 100 International Union Geological Science Heritage Sites in 2022. This is certification by the IUGS. This is the proposal that we made with the colleagues Iaccarino and Montomoli. This is a picture of the South Tibetan detachment in the Rombuk Valley. This stuff is a leucogranite. The dark stuff are sillimanite grade mica schist, and these rocks are Ordovician rocks with fossils, are brachiopods, and so on. And this is one of the first sections that we put in the publication. This is the trace of the two strands of the South Tibetan detachment. This Mount Everest. This picture is from Courthouse and other 2016. On the F1 fault, the lower fault is a ductile one, and the blue F2 is the brittle fault that cross-cut the higher part of the Mount Everest. Here you can see two sections. This section was made in 1998. At that time, publication was in black and white, not color, unfortunately. But you can see here, this cross section was with the upper brittle fault here and the lower ductile fault here. Of course, this is a shared zone with a thickness of maybe 1 kilometer. The upper brittle fault is only a few meters or few dozen meters, no more. This color section made by Max Searle a few years later. You can see the granites here, deformed in the ductile shear zone, the so-called Chomolagma detachment from the Chinese name of the Mount Everest. You can see this dipping attitude, it became flat and flat here. And these two shear zone and the upper fault merge to the north, so that the Ordovician limestone that occupies the top of Mount Everest came into contact with the high-grade gneiss below. Here's just a picture from the Rombuk base camp. The distance is 30 kilometers, so this altitude is more or less 4,500 kilometers. The Chomolagma detachment here and the Lhotse detachment more or less in this position. So these are sedimentary rocks of the Tethyan realm. These are metamorphic rocks and these high-grade metamorphic rocks. Here's another close view picture of the South Tibetan detachment. Here, a Japanese geologist at 8,530 meters in the paper by Sakai and others 2005. This geologist reached the Chomolagma detachment. You can see here the breccias and the cataclysite characterizing the South Tibetan detachment. And of course, it was not the only one geologist almost reaching the top of Mount Everest, or close to the top. And since the detachment is deep into the north, we were able to intersect the detachment more or less in Tibet at 5,000 meters without climbing to Mount Everest, fortunately, unless we are not able to, to take sample. Okay, this the picture that I showed you before. You can see a fossil, a brachiopod fossil here, just in these rocks that are dipping to the north. The detachment is more or less in this position. This is a leucogranite shear the leucogranite, you can see here. In scene section, this leucogranite show a very beautiful mica fish with the top to the north sense of shear, recrystallization of mica, recrystallization of quartz, brittle feldspar, very nice characteristics of this picture. Here you can see the high-grade gneisses with feldspar, biotite, and sillimanite. This is black stuff here. And the Mount Everest is on the right. Okay, this is a sample took just from the outcrop. You can see in the cut beautiful mica fish, C plane, S plane like this, C prime, and this is just LiDAR scanner of the sample. Here's the surface where you can see a little bit better the feldspar, the mica fish, this dark big crystal, the C structure, the S structure, model one. In this section, you have a beautiful mica fish that is this red one. So the sense of shear is very clear. There is a strong recrystallization on the rim of this white mica, and also on the tails of the fish. This stuff is crystallized mica. So yeah, some fish from the book Himalaya Dynamic of a Giant from Gruitz and Kellett. Maybe they made a chapter about the South Tibetan detachment. You can see very beautiful structure everywhere. C prime, sigma type porphyroclast, deformed leucogranite, deformed SCM mica fish also in this section. So the sense of shear is quite clear. And it was discovered by Jean-Pierre Bourg in 1983 during the PhD, just in this outcrop. Because before it was considered only a trust by Chinese geologists, but it was the first to discover this normal sense of movement by studying the kinematic indicators. It was a good structural geologist, of course, one of the first. He was able to change the thinking of this very beautiful. This is a picture made by climbers of the Chapung Tang, close to 8,000 from the Nepali side. And you can see a huge seal of leucogranite here, gneisses intruded by this leucogranite, and the South Tibetan detachment are more or less in this position, and these low-grade sedimentary rocks. There are also samples taken from climbers that are in the museum at Oxford, I think, and some people studied also this sample in scene section. Okay, I show you that sometimes in the Mount Everest section you have a ductile fault and a brittle fault, but it is not so common all over the belt. For example, in this part, just north part of Mount Everest, you have biotite sillimanite gneisses of the dark stuff, mycium leucogranite here, and just above Ordovician limestone. So here you have not two faults, the tile and the brittle fault, but just one single contact of non-metamorphosed rocks above high-grade metamorphic rock. Of course, these Ordovician limestones are a little bit heated by the lower Glitterman sequence and show deformation at the base. This is a picture of the South Tibetan detachment at Mount Choyu. This picture was took by Fabrizio Bartoli, bachelor students in Pisa a few years ago. He was a climber and tried to reach the top. He was not able because problem of altitude sickness, but the colleagues reached the top and collected a few samples for us. And for example, at the Camp 3 at 7,800, 7,900 meters, we found a beautiful small sample with cataclysite. This is the thin section, and thin section you can see levels of cataclysite with grain size reduction by fracturing, characterizing the upper part with South Tibetan detachment. There is also some small normal fault cross-cutting these levels, this cataclysite rich level. So very nice exposure. Associated to the South Tibetan detachment, there are sometimes huge folds. In this section, the Kaligandaki Valley, you can see the Annapurna detachment, the ductile part of the detachment, below the Great Himalayan sequence. Above, you have Mount Nilgiri, and so on. And in the landscape, you can see kilometer scale overturned fold like this, folding the Devonian, Silurian, and Cambrian rocks, very well determined in this part of the belt. So the detachment causes a deformation, a folding deformation, um, overturned folds in the Tibetan sedimentary sequence with a north-east north divergence, of course. Is Mount Ukuche. You can see in this part this kind of fold related to the detachment. This is a reconstruction of the fold, the Nilgiri anticline, and in this mountain that's called Pangnap, you can see an interference pattern because this is F2 folds linked to the detachment, to the normal sense of shear detachment. And here you can see a previous fold related to the one deformation from collisional stage with top to the south movement and fold reversed to the south. So there is a beautiful interference pattern in this part of the belt. So the first phase to the south and the second phase to the north due to the detachment. Okay, so we can give a look to the architecture of the detachment across the belt. Here we are in Dingye, South Tibet. Is an old monastery destroyed by Chinese when invaded Tibet, and the dark stuff is made by high-grade gneisses, sillimanite, and biotite, and garnet. The white are deformed leucogranite, and this is a breccia made of Ordovician limestone. So you have a ductile rock here and brittle rock just above. So these are clasts of the breccia made by Ordovician rocks, deformed by the brittle fall. Just lower, the leucogranites show the same face as all the sheared leucogranites along the South Tibetan detachment. These are beautiful shear sense indicators. In the mica schist, you can see more or less SC fabric to the top north sense of shear. In thin section, you can see mica fish like this, and this pole diagram, they are reported as the C-axis of the quartz that more or less indicate the same sense of shear. Mm. Uh, Here we are going to the base of the Tibetan sedimentary sequence with Ordovician limestones that became a little bit more recrystallized, so they are fine-grained marbles. And in thin section, you can recognize this calcite crystal recrystallized along this layer, making an oblique foliation like the quartz that we observed a few days ago. There are some porphyroclast, sigma type porphyroclast, magnesium enriched clast with a top to the northeast sense of shear. Here we are more or less in marble of the Kaligandaki Valley. There is a strong recrystallization of the calcite crystal with more or less ground boundary migration. There is an intrusion of leucogranites. The leucogranites are sometimes stretched and show abundance. for show some it's called the flanking fold. You can see here this fold above, this fold below. The fold is concentrated only along this piece of leucogranite. So they could be good kinematic indicators, but probably now it is dipping to the left, probably started dipping to the right and was rotated during shearing, causing also the formation of these drag fold that are confined only in this part of the layer. Also common this kind of picture. We are now in Garhwal, so in your country. There are some extensional shear band here, some myelonites here. We took a sample in this part and we dated. There are beautiful mica fish. We are in western Nepal, in Dolpo section. We found big leucogranite stretched and then rotated like delta porphyroclast. There are also some asymmetric folds related to the detachment and strong recrystallization of a calcite crystal, as you can see in thin section. Okay, in Western Nepal, in Kaligandaki Valley, Laura Nania made her PhD thesis with Chiara Montomoli a few years ago and published 3 papers. Now she's working in Geological Survey of Canada. And here we can see in green the Greater Himalayan sequence affected by the shearing of the South Tibetan detachment. In light green, the deformed part of the Tibetan Himalayan sequence. So the South Tibetan detachment affect both the bottom of Tibetan rocks and the top of the Greater Himalayan rocks. The problem that you can see here, there are marble, 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 marble. You have marble of the Greater Himalayan sequence and marble of the Tibetan rocks. So it is very difficult to detect um, the formation, the sense of shear. So we have uh, also in thin section. The same happened in Western Nepal. We have marble and cut silicate of the metamorphic core and the marble of the upper sequence. But we took several samples in a vertical section. Also, you can see another feature. In thin section from the upper part, this is more or less, I think, 800 meters. So the grain size of the calcite is, if you go down, 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 the grain size increases. Do you remember the granite in the Alps with the work of Michael Stipp showing mechanism of quartz? It is more or less the same. It is not a simple granite, but a very hot unit. But the grain size of the marble increases a lot going down up to the boundary with the Greater Mayan sequence and also inside. So, Laura was able to do a very nice work with calcite. Calcite is not so easy as quartz to work with, but he spent several months uh, at the George August University in Germany with Bernard Leys and Chiara Montomoli, working with these rocks. He made the analysis of the z-axis, the y-axis, different axis of the formation of the crystal. So we detected also the occurrence of twinnings in calcite. So from this kind of graph, people are able to build up the sense of shear uh, and also the amount of pure shear and simple shear. It is not easy, and I cannot explain because I need 1 week more to explain this complex. But anyway, there is a paper Nania and others 2014 on physics and 2022 on Journal of Structural Geology that explain very well this kind of work. So for from the fabric of the stereographic projection of the c-axis of calcite, we were able, using the Wenck diagram, to detect the amount of simple shear, pure shear. We have several samples approaching the South Tibetan detachment, going down, the simple shear increases in this way. In this kind of graph, there is a percent of pure shear and kinematic vorticity, and also in this case, from the more distant upper portion, going down, 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 the simple shear increases, um, derived from this kind of complex calculation by c-axis of calcite. Uh, the, this kind of work was made in Western Nepal, Central Nepal, and Southern Tibet, along this section that we collected several years ago. So, approaching the high strain zone, more or less the meaning of this graph is that approaching the high strain zone, the non-coaxial deformation is there is a non-coaxial deformation, but there is an increase in simple shear up to 70%, 75%. So from pure shear dominated deformation up to simple shear dominated deformation. This by calcite fabric. We can use also grain size to gain information about the differential stress that deformed the rocks, because as you know, deformation characterize a decreasing in grain size, so much more stress produce finer grain size. So the grain size is related to the differential stress. So if you take the thin section and you made some measurements of the grain size, the medium grain size. You have, for example, in these samples, the mean grain size is 310 micron. In this sample, it is 420 micron. So you can detect in a quantitative manner the increase of grain size, and you can use this information to characterize the differential stress using some, it's called the piezometers by Barnhorn and other 2004, useful for calcite. In this equation, the logarithm of stress is linked to the grain size d. So if you have the grain size, you can more or less calculate the amount of stress that cause this grain size. And for some sample is from 5 to 15 megapascal. And if you are able to detect the amount of temperature, you can also fix the strain rate, the amount, the velocity of deformation. The strain rate has been fixed by more or less calcite dolomite geothermometers, or by the mechanism of deformation of calcite. So putting 400 degrees, you have the differential stress here, and you have this line that characterizes the strain rate. It's not so easy, but more or less Manaslu Valley, Kaligandaki Valley, Lower Dorpo region concentrate in this part, in between these two lines. Another important feature that you can see an increase in grain size of the calcite. So there is a dynamic recrystallization with grain boundary migration and so on. But above this big crystal, you can also observe some twinings. Okay, and these twinings characterized by calcite, called E-twins, but I cannot go in detail. Uh, Increasing in the width of the twins, and the density decreasing towards the bottom of the shared zone. This is the bottom of the shared zone, so the grain size increase, increase the width of the twins, and the density is became lower. You can see here a higher density of twins, here less density of twins. So uh, you can use these twins to detect the shear stress. There are some methods by Rebaki and others, 2011, a piezometer. So you can assess the amount of stress necessary to 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 determine this kind of deformation that is quite a brittle deformation. Do you remember? It is a brittle ductile deformation, and by this density of twins, you can assess the amount of stress necessary to deform. That is 110, 170 million years, say million years, megapascal, sorry. And it is quite higher with respect to the stress calculated to determine this grain size. So it is necessary much more stress to cause the, the calcite than to cause ductile deformation. There is an explanation for this. Our explanation is this one, that deformation during the South Tibetan detachment can be characterized by two stages, the D2, we call D2 early and D2 late. You can see this line, this the Bayerly law for calcite, this exponential law for calcite. Every mineral has a different um, position of this line. For calcite, this one is the differential stress, the amount of stress, is the depth. So you are here in a brittle condition. There is a brittle plastic transition for calcite. Of course, for quartz or for feldspar is different. Could be different shape. So more or less the meaning is this one. In the D2 early, when grain size increases towards the bottom of the shear zone, you need 515 megapascal to deform calcite because we are in this part of the line. So if you go here, you can find 515 megapascal. There is not the scale here, but the meaning is this one. If you approach the brittle plastic transition, this line moving this way. So in this part, to deform calcite bearing rock, you need much more stress. In fact, we found 120, 170 megapascal of stress. And this is more or less the strain rate. So the meaning is this one, that the deformation concentrated in the marbles in a ductile way, and the rock at the same time moved because we have a normal sense of shear. So the footwall of the rocks, the deformed rocks, moved upward toward the upper structural level, decreasing temperature and decreasing pressure. So from very nice ductile condition, they move in this part in the brittle plastic transition where they need much more strain to deform. There is a strain hardening. So the strain increases, the stress increases from 15 to 10 times more, maybe 150 more or less. In this way, you are able to deform the calcite, but not by crystallization, but only the formation of twins. And this is was made to explain why there is not the brittle fault in this portion of the belt. Because in Lower Dolpo, Kaligandaki, Dinghie, or Marziandi Valley in Manaslu area, you have all you have mainly the brittle portion, the ductile portion, but not the brittle portion as a Mount Everest. And probably it is caused by the kind of rocks because you have a lot of marble and calc silicate, and you can have not a so strong strain hardening, because if you have strain hardening, the formation cannot go away, and the formation jump to another position to deform the brittle fault. In this way, the formation was able to continue among the same levels of the shear zone by deforming in a different way. So this is a possible explanation of this difference along the belt, where in some place you have the ductile and the upper brittle fault, but the rocks are different. You have not calcilicate, but you have gneiss, granites. When you have calc-silicate rock, you have a different behavior, and the South Tibetan detachment, it is developed only in the ductile deformation and in the more brittle deformation, but inside the same shear zone. So it is actually the only one explanation that we found for this different behavior of the detachment all along the belt. So in this way, in this portion, since there is a lot of marbles, we are obliged to use different methods. And of course, we use the calcite with this strange kind of feature. But anyway, the calculation of the position of a C-axis was made by a textural goniometer, so was made automatically, of course, because doing by hand, it's very, very, very time consuming. Okay, so just an example how to work with different rocks. So it is not necessary to go inside the method, but keep in mind that if you face this problem or similar problem with different rocks, there are the possibility to face these problems following this way. Okay, just a few words about the geochronology. Um, we use uranium, thorium, lead on monazite by in situ using laser ablation. This sample is from Garhwal, okay, from Garhwal, India. So these monazite are very nice. The blue color is low yttrium, the red color is high yttrium. So if you date the core of the rim, you have different information. And we add the ages by 19 million years, that are retrograde ages, with garnet plus melt has been consumed, and the yttrium has been released and concentrated along the rim of the monazite. So more or less, these ages could be linked to the uh, ductile activity of the South Tibetan detachment. We had also some ages by argon muscovite by Montemagni, published in 2018, and the ages of muscovite are more or less 16 million years. After that, at 14 million years, there is a growth of the static white micas in the same way to what happened in the main central thrust. So the South Tibetan detachment and the deformation stopped before 14 million years, because you have static micas above the myelonitic foliation. So in Garhwal, the formation is from 20 to 15 million years, more or less, of the South Tibetan detachment. This is a very hot deformation because we are above 500 degrees. This deformation is a little bit at a lower temperature, maybe 400 or 350. So if you remember more or less the ages of a main central thrust, 10, 9 of the Vaikrita, 5 of a Munsari thrust, means that in the same transect of the belt, in Garhwal, in the same part of the belt, the South Tibetan detachment is a little bit older with respect to the main central thrust, that is in between 9, 6, 5 million years. So they are not contemporaneous. So the South Tibetan is older and the main central thrust is younger. So they cannot act at the same time. And this is a problem for all the tectonic model that should be that needs the contemporaneous activity of these two faults. Okay, another problem for the South Tibetan detachment for the ages is this one, the Buraburi granite that I showed you before. Is cross-cut the South Tibetan detachment here because you can find this granite in the Greater Himalayan sequence here and in the Tetian rocks. So it is a pin in the South Tibetan detachment. It is undeformed. We gained the ages of the granite by using monazite and zircon, and the age was more or less 23.5, 24.5. Very nice ages made by Daniela Rubato when she was in Australia, at Canberra. And the main granite, okay, the main granite is more or less 24 million years, and there are some dike, including this kind of dike, including the Tetian rocks, are more or less 23, 25 million years. Okay, you can see a picture from the granite below, the sedimentary rocks. These are dikes emanating from the granite and intruding the South Tibetan detachment. This is a picture of the leucogranite dike intruding the metasedimentary rocks of the Tetian sedimentary sequence. This dike has been dated at 24 million years. So there are, the rock around are really sedimentary rocks. You can see cross-bedding. This level is rich of remain of fossils, Lumachella. And also we gained the age of the sediments by the trital zircons that give minimum depositional age. Anyway, we found ages around 100 and 180 million years. So since these samples are quite close, we put the occurrence of some faults like these, faults and refolded faults, then intruded by the Buraburi granite. So this is really the Tetian Himalayan sequence, low grade, the ages, and below we have the Greater Himalayan sequence. So the age of the South Tibetan detachment should be older than the age of the granite, so older than 25, 20, 24 million years. In this section, the main central thrust activity has been dated at 19 million years by Gibson and others 2016, and 17 million years by Montomoli and others 2013. So the South Tibetan detachment is 24 to 30 million years, and the main central thrust is 19, 17, 13. So very different, very distant ages. That is a confirm that they are not contemporaneous, at least in this part of the belt. So to conclude something about the South Tibetan detachment, we have a complex architecture of the South Tibetan detachment along the belt. Of course, we could expect this because it is very long, very big structure. Moving from east to west, the ductile branch is better expressed. Structure evolution of the detachment. Oh, okay, this is lacking something. There is a plastic deformation protracted at shallow crustal levels that prevent the detachment strain hardening. Uh, so we have deformation, ductile brittle deformation inside the marbles. So lithology variation along strike affected the overall architecture of the shear zone. Marble allow the development of one shear zone, ductile and brittle, where you have granites, orthogneisses, mica schist, migmatites, you have a shift in deformation, ductile below, and a shift, jump to higher position for the South Tibetan detachment. This is common in the eastern part of the belt and also in the North Himalayan gneiss dome. For example, the Kangmar Dome of Yalazambo Dome, they have a brittle portion and a ductile portion below with the same characteristics. The deformation of South Tibetan detachment is characterized by no coaxial flow, as determined by data also authors such as Rick Lowe, Don Kellett, and also our works. But there is a strong component of pure shear. Of course, pure shear decreases towards the high strain zone, where simple shear became dominant, as we can expect. One of the important consequences about the geochronology it is that along most of the study section, MCT and CDS are not coeval, and the diachronicity of MCT and CTDS along the same sections and the occurrence of top to the south compressive high-Himalayan discontinuity could suggest that South Tibetan detachment activity occurred in pulses. So you have ages older than 24, ages 20 million years. So it means that this kind of fault was active in different portions in different times. So now we give a look to the high Himalayan discontinuity in the core of the Himalayan belt. Have you some question about this? This.
I just want to know that in Himachal Pradesh there is one drone structure that is known as leopard. I was reading that paper. That it was saying there is a shear flow which is leopard shear flow, and then being cut by the point that is known as Kolshambo point.
Mhm.
The question is how this shear flow converts itself into a brittle salt structure. Is it a different phases of deformation taking place in that region? And
Yes, there are some paper by Mike Jessup on the Pargil Dome, but I don't remember the ages of the deformation. But I will give a look. Thanks. It's very nice dome. Maybe it is linked to the Karakoram fault also. The extensional jog of the Karakoram fault. So maybe there should be an interaction between the Tibetan detachment and this dextral strike slip of the Karakoram. So I'm not sure if you can compare exactly the ages and the fissure in this part to the other.
my question is like how the shear flow translates itself into a brittle point.
How? Uh, I will give a look to the paper. Thanks. Okay, now we give a look to what happened inside the grid variant sequence. Up to now, we worked on the boundary. Now we go inside. You remember this picture? You have a big shear zone cross-cutting the lithosphere. You have myelonites in the ductile portion. And the fabric in myelonites give information about the kinematics, of course. You remember kinematic indicators, the mechanism of deformation, flow type, simple shear, pure shear, deformation history, and PT condition. If you have the growth of a metamorphic mineral in that type condition, you can reveal completely the PTT condition of the formation of the shear zone. For example, here from this paper with GIAN 2014, we have the growth of white mica and biotite. Here, the rotation of garnet. So the mineral give very useful information using isochemical pseudosection. You can precisely detect the PT condition. But if we deal with a regional scale shear zone, that means shear zone that have duration of several million years and with amount of displacement of dozen to 100 kilometers, we could expect an interaction between metamorphic condition in the hanging wall and in the future shear zone. So there is not metamorphism and deformation, but deformation causes an alteration of the metamorphism, affect the metamorphism of the rock below and above. So long-lasting shear zone can affect the metamorphic paths of the displaced portion in the footwall and the wall. And in this case, we speak about tonic and the metamorphic discontinuity. And this term is intended to be comprehensive of both tectonic feature, including ductile and or brittle zone and the related kinematic indicators, and detectable metamorphic differences between hanging wall, foot wall, triggered by the discontinuity itself. This is a definition that we put in the paper by Montomoli and other 2013, where we firstly published the occurrence of the high Himalayan discontinuity. This is a definition used by the Commission of Tectonic Structure Geology of International Union of Geological Science. So, with the tectonic and metamorphic discontinuities, we have to use different approach, structural analysis, geometry and kinematics, the petrology. You can see here the growth of garnet in section with chemical analysis and zoning in some minerals, for example, or in some element, iron, magnesium, and so on. And you have to also to mix this information with geochronology. So in this way, you can gain the maximum information about the study of the of deep seated shear zone, long lasting one. Okay, and we started to study the Himalayan belt along several transects since maybe 2010. First time that we found this kind of discontinuity was 2010 in Western Dolpo, Western Nepal, lower Dolpa area, but we really do not didn't understand the meaning of this shear zone. So we need several years to try to understand what is the meaning, the age, and the consequences of these shear zones that we found in Western Nepal. We were looking for the formation of the South Tibetan detachment, but we crossed of the belt from Lesser Himalaya to Greater Himalayan sequence, and we found this shear zone in the middle. What is this? Is it detachment? No, the sense of shear is not right. So it was a little bit tricky, and but it was nice to go through this problem. So at the end, we were able to trace this discontinuity from northwest India, western Nepal, central Nepal, Sikkim, Bhutan, for then more than 1,400 kilometers. So the this stuff is a Great Himalayan sequence. This is a higher Himalayan discontinuity here, traced from our paper, our detailed work in the field, but also from literature. And so it divides the Greater Himalayan sequences, an upper portion enriched in migmatitic rocks, and the lower portion that is made mainly by kyanite, garnet, bearing gneisses and mica schist. Is a geological map that we made in western Nepal, in the Mugu Karnali area. This is a Mangri shear zone, our local name. The gem shear zone was just in this very thin portion of the Greater Himalayan sequence. You can see this in this area, the thickness of the Greater Himalayan sequence is very high. In this part is very thin, only 3 kilometers. So there is a strong local longitudinal variation along strike of the thickness of this shear zone. In the field, for example, in Mugu Karnali, we found 3 or 4 kilometers of mylonites. We walked one day in the mylonites. In western Nepal, in the Togem shear zone, we observed a lot of rotated porphyroclast also at the autocrop scale. In this stratigraphic projection, you can see the shear plains deep to the northeast. Red dots are the stretching lineation. It is plunging to the northeast, and the sense of shear is thrust sense top to the southwest sense of shear, similar to the main central thrust. In since action, there is the growth of sillimanite along shear planes, and you remember this picture. There is a grain boundary migration in quartz, a mechanism of deformation at high temperature. There is chessboard extinction, suggesting temperature larger than 600 degrees, so very high temperature shear zone. These are some feature at the outcrop scale, at the macro scale. This is the Badrinath shear zone that we found a few years ago with the PhD thesis of this girl, Beatrix Benetti. She tried to compare the Himalayan belt with with the Brazilian belt in Brazil because she came from Brazil, but his PhD was affected by COVID, so it was a problem to go in the field. But anyway, we took sample before of the Badrinath shear zone. This is this is an outcrop of the Myelonite in the Badrinath shear zone in the road going to the Mana last village. Scene section with the top to the south sensor shear. And now I show you the last example of the high Himalayan discontinuity in the Annapurna Manaslu Massif, in the Marsiandi Valley. In this map, you can see the South Tibetan detachment, Tibetan rocks, sorry, greater Himalayan sequence like this, with the main central thrust. And here in the middle, we found this shear zone that is just in Jagat village here and Jagat village in the other valley. I don't remember the name of this valley, but there are two parallel valleys in the Manaslu Massif, and in the same village there was the same Myelonites. I don't know. It was strange. This is a thrust sense shear zone. There are beautiful kinematic indicators at the mesoscale, especially also at the micro scale. So the sense of shear is the same. The foliation is dipping to the northeast, and the stretching lineation is plunging to the northeast, as in the other shear zone. Another feature that we found in this kind of shear zone is that the PT condition of the footwall are always a little bit higher in pressure with respect to the one of the hanging wall. So there is a difference in 2, 3, maybe 3 kilobars between the rocks below and the rocks above. And the most important thing that the myelonic foliation develops under this part of the path, and the retrograde part of the path. So during the formation of the foliation and the movement of a shear zone, there is a decreasing in pressure. So there is an exhumation of the rock. It is testified by the PT condition detected. This is just one example of pseudosection in Western Nepal. So it's a very complex way to calculate PT condition, but very make some map of the minerals along the thin section and with some complex software, we detect path, the path followed by the rock. Some constrained here, the complete path is an example. Okay, and at this point we would like to know the age of this shear zone. So we use the monazite, as you told you before. This is since of the uh, Eigerman discontinuity in Marciandi Valley. You can see some biotite, some SE structure. So it is show it top to the right sense of shear. We select the monazite under optical microscope. Then we go to the electronic microscope to detect if there are true monazite or zinc or some other things. This is a monazite. Then we made chemical maps of a monazite. This is an yttrium, an example of yttrium map. Blue, low amount of yttrium. Red, large amount of yttrium. The core is depleted in yttrium. The rim is enriched in yttrium. So when we went to laser ablation in Santa Barbara, in California, with John Gotthold, the famous geologist, geochronologist studying the Himalayas and Antarctica. So you can see here the holes left by the laser to catch the plasma to make the attention. So this point for dating were selected just to date the core and to date the enriched yttrium of the rim. Why we use this kind of rock, of methodology? Because yttrium, thorium, monazite, and garnet are a proxy of the formation of metamorphism. So during progressive metamorphism, with the growth of garnet, all the yttrium is sequestrated by the garnet, and the yttrium is show very small amount of yttrium. When so the garnet grow and sequestrate of the yttrium. During the retrograde path, during breakdown of garnet or uh, some other things, yttrium is released in the rocks and is captured, sequestrated by the contemporaneous monazite. So a monazite, a good monazite could show a core depleted in yttrium and the rim enriched in yttrium. This part is related to prograde metamorphism, this one to the retrograde path. So when we date this part, we are dating the prograde metamorphism. When we are dating this external part, the rim, we are dating the retrograde path of the rock, of the monazite and of the quartz of the rock. So we made this kind of work for several shear zone along several transects, and more or less we found sometimes more complex behavior of the monazite because this one are the perfect monazite, but there is mm, some cases where you have a resorption of monazite, new growth, resorption. So sometimes the pattern is not so easy, but if you find some good crystal like this, you can gain the information. And the ages that we found with this methodology, uranium lead thorium on monazite is 25 17, 26 17, 25 18, 27 17. So they are more or less the time span of the age of the HHD in central and western Nepal. We use different laboratories, sometimes in different times, of course. Australia, USA, or a laboratory in northern part of Italy. Now we have an instrument just in Turin, and we are just starting to work with this laser ablation and ICP-MS in these days. So in the future, the next month, I think we are able to date a lot of rocks. And if we compare the age of the main central thrust and this HHD, high mineral discontinuity, we find that along the same section, the HHD is older than the main central thrust, because sometimes in the literature they are confused. If you make not a distinction between these two shared zones, sometimes people put all together or confuse the main central thrust, especially when they are very close. There is not so much distance in between them, maybe 100 meters or few kilometers, such as in Dolpo area, where the thickness of the determinant sequence is only 3 kilometers. And so in these cases, we are able to separate the HHD, that is older with respect to the main central thrust. Okay, I can show you some details of the dating of the monazite. In this graph, there is the number of, uh, of data, and here the age. In red, the prograde path of the monazite. In green, the retrograde path. This is upper GHS, one sample. This is one sample along the HHD in the myelonites. This is so the difference in between the prograde and retrograde path is 28 million years, is 25 million years, and more or less this is the age of the HHD. But if we put all together, this graph is by our data and the data by Jami Wang and other 2018. We can put here the HHD, here the retrograde ages in the hanging wall and the upper part of the shear zone. If we go down in the footwall, you can see the prograde ages and the retrograde ages. What is the difference in between these two parts of this picture? There is a difference. Is a blue color and the yellow color are separated here, and in the footwall it is here. It is more or less 26, 27 million years, and this there is a shift of at least 10 million years in the footwall of this passage. So the rocks above and below uh, didn't underwent exhumation at the same time, but exhumation started before in the hanging wall and later in the footwall. This is the main meaning of this kind of graph. And what is why there is this strange behavior? Because usually people think about the occurrence of the main central thrust, and all the rock of determinant sequence were exhumed. This part we have the hanging wall exhumed before and the footwall later, 10 million years later. The cause is the occurrence of this shear zone, of the HHD, because as a kinematic like this, the footwall, the hanging wall move to the south and the footwall move to the north in different way. So when we activate this shear zone, the rocks below from B1 go to B2 in deeper position. So from this position, the increase in temperature and pressure and go to B2. But the rocks in the hanging wall are exhumed because you can see the arrow. These rocks are brought to the surface. So a rock from position A1 go to position A2. From A1 to A2, there is exhumation, development of foliation, decreasing in pressure and later in temperature in this time span of activity of the shear zone. So this different behavior in the hanging with the footwall is caused by the activity of this shear zone. So up to, from the collision up to 27 million years, it is all right. But at the 27 million years, by the activation of this shear zone, there is a different behavior of the rock above and below. The rock above are exhumed, and the rock below continue to go downward because of this error, because of the kinematic. This rock upper and this rock down. It's okay? So we need a lot of years to understand this, but at the end we found a solution. Okay, numerical models. I give you the information that the Monte Mason were able to build up some numerical models to explain the orogenic the orogen. And so several years ago we asked, is it possible uh, to make numerical models? The numerical models will show only channel flow, or it is possible to show also the occurrence of some discontinuity, such as the HHD. So Andrea Piccolo was a master student in Padova with Manuele Faccenda, that is very strong in this numerical model, and he tried to build up several models to explain the convergence, collision, the strain rate, the PT path of the rocks. So he made hundreds of models. Ecco, this is more or less the movie of one of the models. You can see several points indicating rocks going down in subduction, then coming up by corner flow. And so you can follow the PT path. Oh, of course, this is a very complex model, not easy. So the dark, no, I would like to stop. The dark point, go down to the right. Okay, at this point, there is a situation in which these rocks are going downward and these rocks are going upward. So it is not a very precise model because uh, it is not possible to detect very thin characteristics, but more or less you have an asymmetric orogen. This is a Tibet, very hard part. The orogen is developed only on the southern side, the Indian side. There is the frontal belt, there is a strain rate, the PT are comparable to the one that we detected by PTT condition. And in this way, by rock moving upward and rocks moving downward, it is possible to think about something too similar to the HHD. So that, oh, this 80 kilometers, more or less, in this model, but of course it is not the only one. We are interested in try to think if it is possible to create a different model with respect to the channel flow. It was very complex because there were a lot of thousands of nodes in the model. So to run a model like this, maybe 8 to 9 hours of parallel computer. They rent time in at the Ministry of Research because they have the facility of this kind of things. So we are happy because it was possible. Then there are other numerical models made by Indian geologist Maite Mandal, published in 2021, and they were exactly able to create, to build up the occurrence of HHD in the Greater Himalayan sequence. So I was very happy for this, of course, because as you told you before, in the channel flow, the Monte Jamaison forced the condition. You have a rigid upper plate and a rigid lower plate. You put material coming from India with heating from radiogenic mineral. So you melt, but if you are confident that this melt, the melt of course could move to the south. But if you change a little bit the standard condition, you can build up different orogen, different exhumation models. So it's it's very complex, very complex, but very nice. So of course, Naite Mandal compared with the ages of the exhumation, South Tibetan detachment, HHD, main central thrust, PT condition. So it's a very nice but complex paper because numerical models are usually very complex, especially at the scale of the orogen. So at the end, we can say that HHD is a tectonic and metamorphic discontinuity lasting at least 10 million years, or 27 to 17 million years. which geometry and kinematics affect the PT path of the rocks in the hanging wall and the footwall. Um, in western Nepal, we found also a granitic dike cross-cutting the Mylonites, and we dated this undeformed dike at 70 million years, 16, 70 million years. So at 60 million years, no more deformation along these Mylonites, like the static mica in the main central thrust or the South Tibetan detachment. Petrochronology allowed to recognize the PT paths of the rocks in the hanging wall and the footwall that are diachronous, show diachronous prograde retrograde paths because of the occurrence of this thrust sense shear zone. So if we would like to build up a simplified model of exhumation, up to 28 million years, the rock of the Great Himalayan sequence underwent under thrusting, increasing pressure and temperature. At 28 to 27 million years, up to 17, there is activation of this shear zone, this shear zone in the Great Himalayan sequence. So, whereas the lower part of Great Himalayan sequence continue to went downward, the upper part changed the path and was exhumed, started to move upward. So there is first the exhumation of the higher part of the greater Himalayan sequence, and then at the time of activation of the main central thrust, where this upper shear zone HHD stopped, the formation shifted at the level of main central thrust, 17, 13 million years, 5 million years. At this time, also the rocks in the footwall changed the path and they started to be exhumed. But since this rock exhumed before and this later, we can detect a difference in pressure in between the rock in the hanging wall and the footwall. You remember this graph? Usually in the footwall, we record higher pressure with respect to the hanging wall. That is quite common all over the section. And this could be explained by this by this model. Okay, if we join the information because we are dealing with main central thrust here. Main central thrust, I show you that is made by Vaikrita and Munzeri thrust. I show you already this one, and the formation one after the HHD localized along the Vaikrita thrust at 10, 9, 8 million years. Then the formation stopped at 7, 6 million years because we have the static growth of mica on the myelonites, and the deformation shifted to downward towards the Munzeri thrust nearly at 5 million years. So there is a shift of the formation from the higher parts to the lower parts, dated by precise geochronology. And if we put all together, including the Badrinath shear zone, Badrinath shear zone has been dated at 23, 21 million years because our monazite was not able to catch all the history of shear zone, because in some other places monazite catch the history from 28 to 17. This we are a little bit unlucky, so but more or less the age is the same, but we put what we found, 23, 21. So from collision up to 23 million years, all the rocks were put downward. Then the Badrinath shear zone of the HHD shear zone all over the world, the Himalayas, sorry, started to move. Of course, to exhume this higher part of the rocks, you need erosion, so monsoon, or activity of the South Tibetan detachment, some activity, because you need to put away some rocks above, because only by thrust you cannot exhume. You can to help to be helped by erosion or normal faulting, and then the formation from 20 to 8 million years shift along the Vectita thrust, then along the Munseri thrust. So this is more or less the history that we can build up by HHD, main central thrust, and so on. Okay, this picture is not from the Himalaya, but from the Western Alps. Okay, have you some question about mm, this topic, this HHD, and the last model? Of course, it is quite it is simple, but it is complex because uh, it involves several sections, several methodologies. So you have to work with other scientists. So collaboration is very important because one single man could not do all this all this work. It is just difficult to follow one topic. To follow two or three topics, it's impossible because you have to read the book, paper, and so on. But with collaboration, exchange of thinking, opinion, discussion, uh, it's very, very useful to find a possible solution. Okay. Oh, the method that I mentioned before you, it was tomography, microtomography, because with microtomography, the same that we use for human body, we can put in a small machine some sample, and by several section by X-rays, you can detect the shape of the porphyroclast in 3D without cutting the rocks, and automatically they calculate the orientation, the shape, and we made this kind of work in this paper 2020 on Terranova, because in Milan, at the University of Milan, they have a micro CT, just put on the table, you put a small sample, and after a time they give a result of the 3D organization of the structure, and it's very nice because it's not time consuming. You have not to put lines to detect limits and so on. Uh, you need to have the machine, of course. The problem is that the samples that you put are very small, so you should have a very small porphyroclast. You have a big porphyroclast, you can only put one and so on. Okay. I will give you also some reference paper like this. I have the PDF. I send it to Mahesh, so you have some reference material. And so this after lunch, we are almost left. Okay, we can stop. We will discuss a little bit recall of the model of exhumation, the Himalayan belt. Then we speak about vorticity with an example. Then at 4 o'clock, certificate. It's okay. Have you some question? Feel free to. Hmm. The reason for the formation of the attachment of the normal fault. But do you mean the South Tibetan detachment? Hmm. Ah, at the level in the lower part of the. Okay, there are some possible fault are transverse fault that cross-cut, for example, the main boundary thrust, main frontal thrust. People found this kind of fault also in the Mount Everest area, transfer fault perpendicular to the belt. There are a lot of these with transcurrent movement. And of course, the activity of South Tibetan detachment ended at more or less 11, 12 million years. Then the belt has been affected by rifting or by maybe something that you call Yadong or Kaligandaki Mustang. You have a angle normal fault, more or less perpendicular to the belt, extending the belt. Several structures like this. And of course, this This kind of a fracture are present also in the lower part, maybe the most in the upper part. But for example, if you give a look to the Everest area, you can find a lot of this fracture coming down up to the main central thrust, and so they of course deform the crust in a bit of way because it is already exhumed. So you found a lot of this transversal fault, and so that's very frequent. I don't know about the occurrence. Also, the main central thrust in some places show a brittle deformation inside the myelonate. There are one or two descriptions of this, but it is already in the same sense. And, I don't know if there are some normal fault deep into the south. I think there are some paper. Jit Mukherjee worked in Dauliganga Valley. That is an Indian guy, of course, working in structural geology, now editor of many books, many journals. But he worked a lot. He worked a lot on the brittle deformation at a small scale in the Himalayas. I think there are much more fracture than mapped because we are usually we think about the ductile deformation, but less attention to the fracture. But there are a lot. There are also out of sequence thrust that Samajit Mukherjee detected very well in all over the Himalaya. Also, we found in the Mugu Karnali some out of sequence thrust above the HHD, maybe at 16, 17 million years. So the deformation is much more complex. I show you only one small pieces of the complex history. Some question? Okay. Okay. So thank you very much. Enjoy the lunch and see you after lunch. They, after having seen the main feature of the Greater Himalayan sequence, the South Tibetan detachment, the main central truss, the HHD, we can give an overlook to the exhumation models adopted by for the exhumation of the Greater Himalayan sequence. Okay. Here in this picture, you can see four very popular model to explain the exhumation of the Great Himalayan sequence. And there are differences in the geometry of the South Tibetan detachment, the upper normal fault, and of the main central truss, the lower thrust, bounding the metamorphic core or the Greater Himalayan sequence. In the channel flow model, where deformation should be accompanied by erosion, where a channel of a molten rock move to the south and reaches the surface by the aid of localized erosion on the southern flank of the Greater Himalayan sequence. In this model, the South Tibetan detachment and the main central thrust should remain more or less parallel. In the wedge extrusion model that we saw 2 days ago, these two kind of fault should merge towards the hinterland, towards the north, so the different geometry is a little bit different. A different point of view has been proposed by Alexander Webb, 2007, proposing the wedge insertion model, and for him the grid element sequence is a wedge moving to the south and causing the movement along the South Tibetan detachment as a passive fault. Is a back thrust more or less for him, not a normal fault. And he bases this observation just on this part of the Himalayas where Titan rocks came into close contact with the rocks of the uh, lesser Himalayan part. So the shape of the Great Himalayan sequence is a wedge tapering to the south, not to the north as proposed in this model. Mm. Yeah. For this model, he found only Alexander Webb found a clip of the South Tibetan detachment very close to to the main central thrust. So a few hundred meters or very few kilometers. So going from the inner part of the side to the other part, the thickness of the grid sequence decreases up to, but maybe something similar in Bhutan there is because there are a clip of the Titan rocks very close to the main central thrust. The model represented in C is a critical taper that is a big wedge that in fact not only the brittle portion of the Himalayan belt, but according to Matthew Cohn, it affects all of the thickness of the belt, including the brittle and the ductile portion. And in this way, it is indifferent to the geometry of the South Tibetan detachment and of the main central thrust. Of course, this shape is preferred. Also the deeper part of the belt. This after Matthew Cohn 2008 published in Geological Society of American Bulletin. There are other mechanism of exhumation proposed by people, maybe the Cell, Robinson, Bollinger, and so on. There is thrust and thrust propagation duplexes. In this old paper, you can see that the Titan rocks, the Greater Himalayan rocks, the Lesser Himalayan rocks are put more or less at the same level. There is a thrust of the Titan rocks above the Greater Himalayan sequence. Then the thickening of the belt, development of South Tibetan detachment, and then the movement of the Greater Himalayan sequence above Lesser Himalaya, producing the main central thrust, some antiform and synform to external part. This is a nice model, but it cannot explain the deformation before the movement of the main central thrust, because with this geometry you should have the same pressure at the base of Lesser Himalayan sequence, at the base of Greater Himalayan sequence, and at the base of the Titan rocks. But instead, metamorphism is very different in this part of the belt, and the pressure higher in the Greater Himalayan sequence with respect to the Lesser Himalaya or Titan Himalaya. So this model is good. This is the reconstruction of Western Nepal with duplexes developed in the Lesser Himalayan sequence. There is Ramarg thrust here, a lot of duplex here, antiformal stack in this part, a synform like this. This is Daledura thrust. So this deformation is very good to explain geological feature after the development of the main central thrust, but not before, because before you should involve ductile deformation a lot. This model is not enough to explain all the exhumation. A similar model has been proposed by Sean Long, 2011 in Bhutan. You can see these green stuff are the Tetian rocks. You can see some clip of the Tetian rocks very close to the main central thrust here. So small difference, small distance here or here. So probably tapering to the south geometry of sequence is preferred in this part of the belt. Anyway, when a great element sequence is transported by the main central thrust, most of the formation of metamorphism could be already happened in the Greater Himalayan sequence. So another critical aspect is the geochronology, the age of the formation in between the South Tibetan detachment here and the main central thrust, because most of the model require contemporaneous activity of these two bounding faults as proposed by Godin 2006, Antolin 2013. And these two faults played a major role in several models of exhumation of the GHS, such as extrusion, channel flow, wedge insertion. Okay, if we give a close look to the channel flow, we speak a little bit about this before. According to channel flow, the rocks, molten rocks below Tibet flow towards the south and they go to the surface only by focused erosion. As we told 2 days ago, the deformation is mainly caused by the difference in pressure in between Tibetan Plateau and the external part of the belt. So they cause a migration of the fluid from north to south. As the other component is a simple shear due to the um, movement of India below Asia. So this kind of velocity field, the pressure causes a parabolic shape of velocity field. When we sum up this Poiseuille flow and wet flow, difference in pressure and simple shear, the result is that the upper part of the channel is exhumed because the vector moved to the south, whereas the lower part underwent burial because the arrow point to the north. Okay, and in this way, as I already said. You need in India lower crust, very strong, an upper crust in the Tibet, very strong, the blue one. In this model is able to explain several things, the formation of granites, maybe in the upper part during the motion of a partial molt zone, inverted metamorphic sequence along the main central thrust, the erosion that act together with tectonics. And this model is based on several observations. For example, I took into account the velocity of the formation, the denudation front, the amount of material taken away from the rain, the monsoon, the radioactive heat source of the sediments from Indian plate coming in subduction, because there is more or less 2 microwatt for cube meter. That is very important, this heat source, because to melt this crustal rock, you need not only to reach depth of 20 kilometers, 30 kilometers, because they are not enough to melt so largely the sediments, but you need also an internal heat source for the Indian plate. And maybe this amount of heat source is overestimated, because there are later paper demonstrating that the heat source is not so high from the sediments from the Indian plate. So they take account also um, the the shape of the isogrades here and below. They compared the PT data from real rocks, the black one of temperature and of pressure and of temperature, and the green and the red dots are from the model. So there was a good coupling between natural model and model and the data from the model. So they build up different PT path for the lesser Himalaya, here for the greater Himalaya, for different part from different rocks from different portion of the Himalayan belt. And at the end, but they forced the upper part, the yellow, lower part to be very strong. So this part could melt and move to the south by the difference of pressure and it be exhumed. In this other picture, they made the same people, Beaumont and others, made some experiment, and if you have this initial picture with no denudation, no focused erosion, the channel remain in depth and move only horizontally. By the help of efficient denudation along a strong raining and erosion in the frontal part of the belt for several million years, the velocity of the rocks is not horizontal, but start to move towards the surface, so the rocks are exhumed. With no efficient erosion, you have a lot of faults here, but the the channel remain in depth with no exhumation. So more or less, and in some way they are able also to explain the post-exhumation evolution with the deformation of the gneiss dome that now occurs in the Tethyan Himalayan rocks, the North Himalayan dome. Okay, just a recall, this kind of model could explain the inverted metamorphic sequence um, along the main central thrust with a telescoping of this ograd just along the thrust or along the South Tibetan detachment, but in this way the isograd put in a normal situation. And what we observe now at the frontal part of the belt, there are rocks that were molten 20 million years ago. Now the molten rocks are below Tibet, and it was due mainly by the seismic profile made by Nelson 1998 from India to China. They found several low velocity zone, but after this experiment, this profile, some people found that these molten rocks are not expanded all over the subsurface of Tibet, but they are concentrated mainly among the rift, such as the Yadong Rift or other rift. So there is no a melt layer all over across the subsurface of Tibet. Uh, these are the main characteristics of a paleo of a channel flow and the exhumation of the paleo channel. Of course, you have the limit, the 650 degrees centigrade, the isotherm, that is a boundary of solid also to melt rocks. After above the rocks are molten and below the rocks are under solid state. So there is the frontal part of the channel is a crystal block made by solid rocks that are extruded. So you have channel flow and the extrusion of solid rocks by the action of the normal fault and thrust fault, aided by erosion. Some people proposed, such as Larson and Hadar, a Canadian geologist, proposed a modification of the channel flow, including the channel flow in the critical taper model. So they more or less adopted a model similar to Webb for the South Tibetan detachment, that is backthrust, in fact, not really a normal fault. And these rocks, this molten rock, pull ahead and cut through the crust, uh, causing the formation of the South Tibetan detachment here and the main central thrust below, up to the exhumation of the rock. So for them, the difference in pressure is able to break the rock up to the surface. So this is a mixed model, but it is a qualitative model without quantitative evaluation. I would like to stress some feature because in the channel flow model, the incubation period that is required to increase in average crustal temperature to generate a low viscosity is between 10 and 20 million years. So you need much time to melt the rocks below Tibet from the beginning of the crystal thickening from the collision. This implies that all GHS should be molten at the time of the flow. So it needs to be all made by molten rocks. This means that you need to find migmatite everywhere, from main central thrust up to the detachment. But it is not really true because the first unit, unit 1, is made of kyanite, garnet kyanite bearing gneisses that deformed under solid state. There are no migmatites at this level. So it's just a first problem. The production of melt, leucosome, rival with the channel flow, must be younger than the shortening structure in the overlying log, so the Tibetan Himalayan sequence. Another very important thing is that an active channel must be 10 to 20 kilometers thick to go ahead in an efficient way, because with lower thickness, lower time, the model cannot produce the channel flow. But as you shown before lunch, the thickness of the grid sequence change a lot from west to east. Thickness changes to 10, 4 kilometers, maybe 13 kilometers in Bhutan. So not in every section there are the condition to produce the channel flow. The channel flow would have horizontal transport bigger than the vertical one. So it is difficult to explain the production of eclogites that needs large depth. Is a problem. This is a nice thing because in channel flow, vertical transport is allowed by localized erosion by the monsoon. Otherwise, the flow remains below the surface. So it was the first paper to stress about the importance of erosion in helping the tectonics. And the last thing is that main central thrust and south beta detachment should be contemporaneous, but it is not really true all along the belt. For example, in India, in Western Nepal, they are clearly developed in very different times. So we could give a look to this model. On the left, you have the model that require the South-Tibetan detachment and main central thrust to be contemporaneous, channel flow, wedge extrusion, and wedge insertion. So this model cannot be applied all over the belt because the different timing of this normal fault and of main central thrust along the same sections. In this model, the critical taper or in sequence shearing, the contemporaneity of these two boundary fault, the upper and lower, are not necessary, are not required. So they work without this feature. Okay, we come back a little bit to the in sequence shearing model that we examined this at the end of this morning. Um, The GHS is not a coherent tectonic unit. A coherent means that is a solid unit without a deformation inside, without discontinuities. But there are shear zone in it with top to the south and southwest and south shear, such as the HHD that I show you this morning. And another shear zone that we found within the Great Himalayan sequence is in central Nepal. They so-called Kalopani shear zone in Kaligandaki. Kalopani means black water in Nepal. Uh, and in this small village, we found that is a very high part of the Himalaya, of the Great Himalayan sequence. We found a beautiful shear zone just along the road, but also away from the road, that was active in between 41 and 30 million years under solid state condition with no melts inside. The melt migmatite occur only in the upper part of the Great Himalayan sequence. We have the high Himalayan discontinuity, HHT, active between 28, 27, 17 million years that separate the upper migmatites from the lower kyanite bearing gneiss. So if we make a very schematic cross-section through the Himalayan belt in the central Nepal, there is main boundary thrust, the main central thrust, the lower and upper, the HHD, the Kalopani shear zone in this position, and the South Tibetan detachment. So it is really a unit characterized by different shearing up to the south, but to different condition of pressure and different ages. This is the geological map of the Kalopani shear zone. This is more or less we are along the Kaligandaki River. This Kalopani village. If we go ahead, we reach Mustang, Upper Mustang, then China. Here you can see the trace of the South Tibetan detachment with marbles. South Tibetan detachment. Here, this guy is Lorenzo Gemignani that we left for 2 months in the mountain to map the South Tibetan detachment and the Kalopani shear zone. So we have here the unit 3, the upper part of the Greater Himalayan sequence. This is more or less the thickness of the Kalopani shear zone. Scattering orthogneisses, calcasilicate gneisses, and also mica schist. And we took two beautiful samples here in the mica schist, garnet and starolite mica schist, and in the orthogneisses here. Here the orthogneisses of the upper part of the Greater Himalayan sequence, deformed by myelonitic foliation with more or less SC structure and rotated porphyroclast with top to the southwest sense of shear, so contractional shear zone. So it is a novelty, this one, because is a contractional shear zone. Just you can see the scale here is 1 kilometer, 1 kilometer, 2 kilometers. So we are very close to the South Tibetan detachment, not so much a distance, but we expected to find some normal deformation. Instead, we found a contractional deformation, top to the south. We dated these samples, this since action of the garnet bearing staurolite. You can see beautiful garnet. We found monazite, this small crystal inside garnet, and the monazite along the main foliation. And we analyze this monazite with the same methodology. I map, chemical map, laser ablation, and ICP-MS connected. This was made in Italy, in Pavia laboratory with Antonio Langone. In this rock, you have garnet, white mica, biotite, staurolite, plagioclase, ilmenite, and so on. Plus monazite, apatite, and zircon. We dated zircon and monazite from the orthogneiss here, and the zircon and monazite from the mica schist. You can see some holes from laser ablation. Then we analyze the same with another methodology with the Nella Rubato to be sure of the result, because we found very old edges, and we are a little bit surprised of this. So we applied two different methods, and we published this in 2016 Geological Society of America. In this uranium lead diagram, you can see the ages of the orthogneiss. Very nice concordant ages at 41 million years for the monazite along the main foliation. This is a sample from the mica schist. The red stuff are related to the monazite along the myelonitic foliation. This yellow along the staurolite, and the green inside the garnet. As you can see, the monazite inside the garnet record all their ages, 48, 43.8 million years. This is related to increasing pressure and temperature of the garnet. So more or less the stage of prograde metamorphism after collision. And instead, the red edges, this one and this one, is along the foliation that are concentrated in between 41 and 30 million years. And this is a PT path of these rocks. So you have the pressure here, the temperature here, the possible path considering the composition of the white mica, so the garnet, all the constraint of the magnesium content in garnet, the calcium content, the silica content in white mica. So we are able to establish that this part of the path has been related to exhumation, and this part developed during the D2 formation, the formation of the shear zone. So this path has been constrained between 41 and 30 million years in this part. Okay. So if we put also this shear zone in the in-sequence model, we can see that the grit element sequence, comprised between the Titan rocks and lesser Himalayan rocks, is divided in three portions, three panels. The first one is comprised by the Kalopani shear zone and the future South Tibetan detachment, because at 41 million years the South Tibetan detachment was not yet active. The second panel is between the Kalopani shear zone of the HHD, Higher Himalayan discontinuity, that in this section of the belt has been named the Chomrong Trust, but it is present in the Kaligandaki. And the third panel is the one comprised by the HHD and the main central trust. Mm. So the exhumation is different in between each of these panels, happened in different times with the same kind of mechanism, but in different times. Okay, with up to 41 million years, we had the undertrusting of the Indian crust below Tibet, so regrade metamorphism with no other things. Some ages record the deformation between 48 and 50 million years inside garnet, but no very good information about the kinematic. At maybe 41 million years, this deformation, this shear zone localized here. We don't know why. We don't know why deformation just choose this place to develop. It is an open question. And with this activation, we can do the same as the HH did this morning. And with this kinematic, this arrow, you can bring the point A is started to move in this position, increasing pressure and temperature. This part is inferred. This part has been calculated by TPT condition. At this time, the path changed, and this rock start to move upward. So underwent exhumation. Of course, it means that at that time there was erosion, some normal fault above. There should be somewhere because we have no information. There's also no information if at 41 million years the belt was already uh, uplifted and underwent exhumation, erosion. But anyway, something happened because the pressure was decreasing at this time. So, mm, oh, maybe another possibility is the ductile distributed thinning. You remember from 2 days before, explained the mechanism by Shenlong. He showed that by simple shear and pure shear, you thin the critical remnant sequence, so the pressure could be lower and could explain part of the exhumation. So one of these three, erosion, normal faulting, or ductile thinning, could be active to exhume the rocks, the upper part. So the exhumation started in the uppermost part of the GHS. Then we have no more information after 30 million years. No dating, nothing in the rocks. Was cooler than so more deformation. Then deformation shifted towards the HD between the 26 and 18, 17 million years. So also the point, the rock in B in the middle panel start to be exhumed later than the upper one. So this rock start to move in this direction. At that time, we should had the intrusion of the Buraburi granite here. So means that in before 24 million years, there was an activation of the South Tibetan detachment, probably helping the exhumation of this the panel, this Eiger panel of the Great Himalayan sequence. Then there are younger granites at the 20-90 million years, such as the Mugu granite in western Nepal. So this stuff become exhumed this earlier, this later, and then the point C continue to be under trusted increasing pressure and temperature. Only at the activation of the main central thrust, all the rocks in A, B, and C were exhumed, but this started before, this later, and this later again. At this time, activation of the main central thrust, I put just the AZ, but it depends on the cross section of the belt. lesser Himalayan rocks become involved in the belt, underwent increase in pressure and temperature, and then they were exhumed by the main boundary thrust or Berinag thrust, some other lower thrust, diciamo, lower position with respect to the main central thrust. The problem is that after this, there is not much more metamorphic minerals to detect the PT condition. But anyway, this could be a more complete view to explain the in-sequence shearing. There are some problem because we try to find this shear zone elsewhere in the belt, such as in the Makalu region or Manaslu region. But it is a big problem because here, if you give a look to the map, you have calc-silicate gneisses, calc-silicate gneiss, mica schist, marbles. You have not a huge intrusion of granites or migmatites. So probably this part of the belt, no, I have not the picture that I'm looking for. This part of the belt preserved this older shear zone because there was not so much melting and not so much intrusion of granites in other places, such as Noops, Makalu, or some other section. There was a lot of melting, so the rocks were completely molten in the higher part with intrusion. So the structure was more or less destroyed. This particular place where up to the South Tibetan detachment we can observe this activity of this older shear zone. But anyway, the data the data are in favor of in-sequence shearing model because we have the Kalopani, HHD, upper main central thrust, lower main central thrust. So when we gain information of the age of the shearing, it is moving to the south in sequence way. So probably it could explain the exhumation and the different timing of exhumation of different portion of the greater Himalayan sequence. Okay, this is from Ladakh. Do you know? Okay, have you some question about this just overview of the models? So, of course, models are very simple. I simplify the reality of the rocks and of the Himalayan belt a lot because probably also out of sequence thrust was efficient to work sometimes because we have some out of sequence thrust even in Western Nepal. We found these. There are also transverse faults and so on. So the way to well understand the origin is very hard, but the take-home message from this kind of work is that to work accurately in the field to detect the the shear zone, the faults, to collect oriented sample, to analyze at the macro scale, to gain information about the pressure, temperature, good methodologies for biochronology, mainly maybe the same methodology uh, to date the rocks because they use argon-argon on hornblende, on plagioclase, on white mica, zircon, monazite. Probably they gave different ages, so it is important to use the same methodology and the same minerals to gain the right information. And the two mix, of course, much more methodologies, much more information to build up some possible models or try to understand in a better way your data. You need to have a good data. The data should be very nice. reproducible. Each people go there, uh, take the sample, take with the methodology, obtain the same results. And this is a very important point. Then you have to discuss this data with other people, other colleagues, and to try to best interpret your data, taking, of course, in account also data that are not in favor of the model of what are you thinking, because sometimes people tend to overestimate his own data and not to take into account the other data. So this is just a very, very simple model, but I think it will be a lot of time to go in to well understand the Himalayan belt because it is very big and not known in every place. For example, 10 years ago, we found this huge granite with people never found, never mapped. So maybe also along the belt we have different maps with different classification of rocks or units. So this is also a problem. But also, when people apply numerical models, should take into account the natural data. Because for my experience, when you put a number and models, you can build up what to do you want, no problem. But if you put good data, you can try to build up more nice model. And of course, there are many, many variabilities, many, many factors. I remember the thesis of Andrea Piccolo was 100 pages with 130 models, and the first 30 pages were devoted to the parameters, to define the single parameters. So maybe dozen and dozen of parameters. If you change a little bit one number, change a lot the final result. So also numerical model are very nice, but they should interact with the data and with the people to try to find the better explanation. But they help because when you go in the field, you see only uh, the last picture of the movie, but you lose completely all the history. With the model, you can gain information about what happened since the beginning. So you think about several parameters, and so they are very useful. Okay. Yep. Yeah. 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 Um, Usually, the leucogranites in the Great Terminal sequence are think to came from the molten part of the Great Terminal sequence. The geochemical constraint about this. And this morning I showed so the Makalu granite, where there are a lot of dikes that increase in volume up to the upper granite occupying the upper part of the Makalu. So also in the field, you can see really a large amount of dikes that increase, and at the end build up large volumes such as the Napsi granite, the Makalu granite, or the Buraburi granite. So because here you have the temperature enough to melt the rocks, the crustal rocks, and so the origin should be more or less in this part. Thanks. Some other curiosity? Hmm. Along the MCT, just above MCT, yes, but cross-cutting the MCT, no. I never found, unfortunately, because mm, mm. but not yet. Okay. So you have not question? We can. Oh, okay. So. Mm, mm, mm. Uh, okay, I think the chemical signature of this granite is crystal. I remember amount of strontium or other elements. So geochemical analysis of most these granite are from crystal origin, not mental origin. Also in the leucogranites in the North Himalayan gneiss are very similar to this one, leucogranites. So maybe in some uh, in some metamorphic domes, such as the Yardoi dome in southern Tibet, there are some very old granite at 45 million years that could show some mix with something from mental, I think. And they are very strange because they are undeformed. The Yala Zambo dome is still a problem. Mhm. Okay. So now we have to do something with vorticity, the vorticity of the flow, with some one exercise maybe, because we spoke about vorticity several times, and then we could go a little bit into depth for this topic. So we will deal with the vorticity of flow, some methods and applications. Some application I show you before, but just a recall of what is the vorticity. The vorticity is defined also in a mathematical way, but I avoid to, to give you this boring stuff. Anyway, there is a nice paper by Paris Xipolias, 2010, published in Journal of Structural Geology that make a nice review of the vorticity methods. You can find also in the Pasquier and Trau book, but I will give you the PDF together with other references. So if you are interested, you can go into depth of the vorticity. I remember you that vorticity is just a method to estimate the amount of pure shear. You can see here the coaxial deformation, pure shear, where during deformation the short axis and the long axis remain in the same position with no rotations in in a field of deformation. And simple shear where all the line rotates in the direction of the shear. If you mix these two type of flow, you have the general shear or non-coaxial deformation characterized by both simple shear and pure shear, such as intranspression, intranstension. The end member is the simple shear where vorticity number is number 1 equal to 1, and the pure shear vorticity number is equal to 0. In between, the different values are comprised between 1 and 2. Mm. Okay, if we give a look to this picture, we can see pure shear, non-coaxial deformation, simple shear, and you can see also this kind of line, the thick black line that has a apophysis of the flow. This means that during pure shear, you have all the particle in the field of deformation that follow an hyperbolic path like this, is rotation to the right, rotation to the left, rotation to the left, to the right. Only along these two lines, the particle follow a straight path with no a curved path. And these two lines are called apophyses of the flow. During simple shear, you have only one apophysis, the horizontal one, the one parallel to the shear, and the second one vertical disappeared. In between full shear and simple shear, these high angle apophyses rotate in this direction. In destral shear, it rotates to the left, and this angle between this apophysis and this one is related to the non-coaxiality of the formation. So vorticity is equal to the cosine of this angle. Mm. So it is very important, but okay. So the apophysis of the flow are very important for this one. You can see here the particle path impulse shear in this movie made by Fossen. You can see all the lines move along curved path. Only along this apophysis of this one, the particle moves in a straight way. So at the end, these two blue line are the apophysis. And the angle of the apophysis is 90 degrees in pure shear. This is simple shear, Dexter simple shear. And the particle moves parallel to horizontal axis and does not change the position along the vertical axis. And you have only one apophysis. So alpha is equal to 0. And the situation is this. When you mix simple shear and pure shear, you have combined situation. All the particles move along curved lines only along this this black line, the particle moving in a straight way. This is a stable apophysis that is parallel to the flow, parallel to the shear zone, and this is the unstable apophysis, the ones that rotate from 90 degrees to parallelism to the other one. So in this way, this angle is related to the amount of vorticity or the amount of pure shear and simple shear of the flow. Non-coaxial deformation is typical, of course, of a shear zone, but also between convergent plate, where the convergence is oblique with no uh, um, straight collision, but when they move obliquely each of the other, the plate. So the internal part, this internal part of the formation is characterized by both simple shear and pure shear. So there is a general flow. In this graph made by Reclos, you can see here the vorticity number from 0 pure shear, 1 simple shear. The 50% of pure simple shear is put at 0.71. That is, in this situation, you have the 50% of pure shear simple shear. In this part, you have the formation dominated by pure shear. And in this part, deformation dominated by simple shear. Simple shear is much more important. You can see the same in this much more simple graph. Start from pure shear, general shear, equal amount, and simple shear dominated. So just to have an idea. Okay, now we go a little bit inside the flow of the formation. I avoid the mathematical part because it's very boring, but you can find in the mm, in the paper by Cipolias, this one. Mm. So in one deformation, you have the instantaneous stretching axis, The instantaneous stretching axis are more or less the deformation that happens instantaneously. So you have the shortening axis, extension axis, and the axis, maybe X, Z, and Y. And in this case, the vorticity vector is parallel to this axis. Okay? So the physical meaning of vorticity also could be expressed in a mathematical way, but it is equal to the sum of the angular velocity of any pair of instantaneously orthogonal material line in the vorticity profile plane. So you should be perpendicular to the vorticity vector, and if you take in consideration the angular velocity of this line and this line, the mean value is more or less the vorticity of the flow. It is also twice the average angular velocity of all material lines lying in the vorticity profile plane, and it is twice the rate of rotation of a rigid spherical particle in to clearly deformed matrix. So these are the definition of vorticity, but the amount of simple shear and pure shear is much more easy to remember. Okay, just we spoke about the monoclinic and triclinic deformation. The easiest way to deal with vorticity is to consider the vorticity axis, rotation axis, parallel to one of the deformation axis of the instantaneous ellipsoid, one of the ISA, usually the y-axis. And if this axis is oblique with respect to the ISA, we deal with clinical deformation. It is very difficult to find and also to deal with. But for very high strain, usually the vorticity is parallel to the intermediate axis of the finite strain and also of the instantaneous stretching axis. And this helps a lot to reveal the deformation. Okay, we can go ahead with this. Okay, we have to distinguish in between vorticity K and vorticity M and N are different point of view of the vorticity. This is instantaneous vorticity, this is finite vorticity. This is another kind of vorticity that we can consider when there is increase in volume of the rocks. But anyway, if you are in this condition, monoclinic flow, plane strain condition, no deformation along the y-axis, and the steady state deformation, that means deformation is constant through time, all these number, Wm, N, K, are the same. So we put in the more simple condition. Okay, so monoclinic flow, steady state deformation, and plane strain, no deformation along the intermediate axis of deformation. Let's just be correct. Uh, just a look to the vorticity, pure shear, vorticity equal to 0, 0, 1 vorticity is a general shear, simple shear vorticity equal to 1. If a vorticity is large to 1, and from 1 to infinite, more or less the path are elliptical of the rocks. If vorticity is infinite, the particle is circular, and we have a rigid body rotation. So, but this is not only the only one flow that you can find. There are other strange kind of flow, but I avoid to put just not to confuse much. Okay, so in a flow you have apophysis of the flow, and the instantaneous stretching axis. The apophyses are the straight line followed by the particles when they move during the formation, and the instantaneous stretching axis are the direction where material is extended or shortened instantaneously at each instant of the formation. So, is when you deal with a flow in a shear zone, for example, in a transpressional shear zone with simple shear and pure shear, you have the stable of apophysis, this one A2, that is stay parallel to the shear boundary, but I cannot see the apophysis in the rock, of course. And the other apophysis, A1, make an angle alpha with the stable apophysis. Okay, this is the apophysis of the flow. Then there are the instantaneous stretching axis, shortening, elongation, direction of deformation at each moment of the deformation. And then there are X, Z, and Y that are the three axes of the finite strain ellipsoid. Mm. So there are three kind of axes. The finite strain ellipsoid, so that the X, Y plane mark the foliation. It is the only one thing that I observe in the rock. In the rock, I see the foliation that is the trace of the X way foliation. It is a physical thing. The instantaneous stretching axis I cannot see. I cannot see only some structure related to this one. And also the flow apophyses are not easy to observe, of course, in the rock because you cannot see the displacement of the particle. So it is not easy to deal with this object. The vorticity is the cosine of the two apophyses. So if it is possible to see the apophysis in the rock, I can calculate the cosine of this angle and I have the vorticity, so much more problem, but it is not so simple. In this case, what is the difference between this and this one? What difference do you see? The angle alpha is changed and also the A the A2 apophysis is rotated in this position. So, and you can see also this arrow. So here you have shear and compression, so transpressional deformation. Here you have shear and enlargement, stretching. So there is a transtensional deformation. So it is exactly the same situation, but rotated of 90 degrees. So usually these angles are small and these angles are quite high. So this elongating shear zone parallel to the shear on the left, and this elongation is perpendicular to the shear. So sorry for this question, but it is a little bit important for the flow because when you have non-coaxial deformation and you can calculate the vorticity and you have a strain marker such as conglomerates or deformed cluster and so on, you can put all together this information, vorticity and strain, and by this apparently complicated equation, but it is not really complicated. You can put in this equation here the vorticity value, maybe 0.7, 0.7, 0.7, and here the axial ratio along the XZ section, maybe 4. You solve this um, equation and you find S. S is the shortening or the stretching along the shear zone. Of course, you have a positive stretching in vertical and a negative stretching in horizontal that is extension. So you can calculate how much material is extended due to vorticity and strain. You remember the cake effect, like a toast with marmalade inside or jam inside? You you shorten and the marmalade go away. In this way, you calculate exactly how much material could put in elongation along the shear zone. And this method has been used by the Don Kellett, Rick Lowe for the South Tibetan detachment, also in some paper, also in Argentera in the Variscan shear zone. Uh, It's useful because if you have these two values, you can combine and calculate the amount of extrusion, lateral extrusion. Okay, this graph is more or less vabbè, is more or less the same. You have shortening perpendicular to the flow plane in percentage and extension parallel to the transport direction. The red line is for no stretch along Y, that is plane strain. But if you have constriction, you have this kind of line, and flattening, you have this kind of line. But okay, you can use this equation with no problem. So after all these complex things, we can start to give a look to the method to calculate this vorticity analysis. This is nice, has been developed by Grasemann, an Austrian geologist, who worked a lot in this part of the Himalayas. And he found that in tension gases and stylolites, you can calculate the vorticity because you know that these veins are formed in this position, then rotate when the formation go ahead, so they are not more able to open in this direction, and the new fracture form according to the sigma 1. So the tension gases and also the stylolite. The stylolite, remember that the peak of the stylolite are more or less in the direction of sigma 1 or in the direction of the shortening. So Grasemann found, Bernard Grasemann found that the initial angle of these tension gases is parallel to instantaneous stretching axis 1. So at each instant, you have a direction of shortening, direction of extension, and these lines are parallel to the instantaneous stretching axis 1. So if you, it is simple, if you take consideration the angle between this initial line and the fall plane, for example, C is 8 degrees, the sin of 2 times um, epsilon, epsilon is 0.7. So the vorticity in this kind of object is 0.7. 0.7 means close to 50% of simple shear and simple shear. 50% is just 71, but 0.07 is close to maybe 49. This is very nice because in the field you observe very frequently tension gases, rotated tension gases. So if you have a lot of these, you can also calculate vorticity also in brittle ductile condition with no much more complex calculations. So keep in mind this possibility. If you are interested, there is this paper by Grassmann and a paper by Fossen and Tikoff, 1993, on the Journal of Structural Geology. Anyway, in this review by sorry, by Paris Xipolias, this method is reported and described. Okay, when we go in the ductile field, we sometimes we need to use the quartz C-axis fabric because uniaxial crystals such as core quartzite are very useful to characterize the formation. So, for example, here you have the C-axis of quartz as a main axis oriented in different ways, so an isotropic situation. After deformation, you have the slip along slip plane in the quartz. So the z-axis move, and of course, it doesn't go in the same orientation, but it show a pattern that is characteristics. For example, after deformation, simple shear deformation, you put in this way and in this way. So from this kind of a pattern, it is possible to calculate the sense of shear, but also the amount of vorticity of the flow. For example, when you make a lot of measurement of quartz, you can have a symmetric distribution. So all the points are put in this shape. You have a symmetric distribution, maybe pull shear, or an asymmetric distribution like this that is related to non-coaxial deformation component of simple shear. So it's useful. Uh, it is called quartz vorticity gauge. You can have oblique grain shape fabric in quartz. You remember the ribbon quartz of the Milonite. If you take this orientation, you can gain information about several things. Also, the C prime type shear band are very useful because they are related to the instantaneous stretching axis. I go. Okay. I show you 2 days before how C prime works. If you have this stable apophysis in the flow, this unstable apophysis, the one that rotate according to, and usually the maximum shear strain is bisector of this angle. This means that C prime shear band developed in this direction because there is a maximum shear strain. So it is very easy. You can take a measurement of this C prime with respect to the high strain foliation. You double this angle and you find the vorticity value, the cosine of 2 times 38 degrees, that is this angle. Of course, the problem is that sometimes this C prime shear band rotate, so you can see a lot of measurements here, and you can take some 10, 20 measurements. You take the highest angle because probably they are the ones that are formed parallel to the maximum shear strain before rotation. When they rotate, the angle is lesser and lesser, so you take the highest angle. This is another way, another very simple way to gain information of a simple shear in myelonitic rocks with C prime fabric. It is quite common. You can see also in the field in polished slab of rock. Okay, the limitation of the methods that we use is the assumption of monoclinic flow with vorticity vector parallel to the y-axis. This assumption should be checked. The way I check is to observe this section, this the vorticity plane, the XZ section, to observe here if there are rotations. If there are rotation, probably you are oblique to the vorticity axis. You are not in a monoclinic flow, so you have to do some very complex thing to left the sample or put the sample away. So this rotation, okay. In this section, you must not observe rotation if you are in monoclinic flow. Okay. Do you remember when I show you the shear zone? I show you the behavior of the object. Axial ratio increases with shear, and the angle decreases in intensity as strain increases. In this graph, you can see the strain ratio and the angle of the long axis of the strain ellipse. if a vorticity change, you have different path of the angle, and you can in this kind of graph you can mix the axial ratio and the angle. You you obtain the axial ratio of the finite strain ellipsoid here, the angle in between the the long axis and the shear zone. You can put in this graph, for example, strain ratio is 10, the angle is 10 degrees. You are in this graph that is more or less vorticity close to 0.9. So high strain simple, high prevailing simple shear. Mm. Because these angles are different from the angle followed by the, the strain following, diciamo, deformation not characterized by non-coaxial deformation. So more or less the vorticity can be obtained by this equation, this angle, this axial ratio. You can use this equation or this graph if you have diciamo, a good idea of the shear zone boundary. Of course, if you are in a field in a colorimetric scale shear zone, this cannot be applied because you cannot see the shear zone boundary. You can observe the myelonitic foliation, but to the micro scale, it is not exactly parallel to the shear zone boundary. There is always an angle 1, 2 degrees. So in shear zone where you can see the boundary very well, you can apply this method. Okay, if you cannot see the boundary of the shear zone, but you have object deformed, you have the macroscopic foliation, the magnetic foliation, the amount of deformation, so you have the ratio xz, you can gain the information uh, of the shear plane using the z-axis of quartz. So you have to put the thin section under the electronic microprobe with ABCD, backscattered electron. They can measurements of the axis. They project in a stereographic projection. You can find the skeleton, this kind of figure that is characterized by the quartz. So you are trying to define this kind of a skeleton uh, in the projection of a z-axis of quartz. And in the central part, you have to join these two maxima, and the perpendicular line to these two maxima is more or less the shear plane, because experimental works and natural observation found that this is a useful method to calculate the shear plane, because as shear goes on, the z-axis of the quartz are oriented perpendicular to the shear plane. So you can use the z-axis, the central part of this girdle, to obtain the perpendicular, so you have the shear strain. So you can measure the angle between the macroscopic foliation that you can plot the stereographic projection, and this yellow angle is a beta angle between the shear plane and the macroscopic foliation. So you can use the previous equation with no problem. So uh, you have to use z-axis of quartz. Okay. Ah, and going backward. Okay, if you have oblique grain shape fabric, such as the ones that we observed in the myelonites of the Kumbu in the thin section, you have ribbon quartz with oblique foliation. You can use this oblique grain shape fabric because when you have an oblique foliation, the grain of quartz start to grow parallel to the instantaneous stretching axis, the extensional instantaneous stretching axis, then rotate into parallelism to the shear boundary, and then re- restart to recrystallize. But when they start to crystallize, they are parallel to the instantaneous stretching axis. So you can measure the long axis of this subgrain or oblique grain. You put in a histogram. You can, of course, use you needed to do several measurements. There are angles varying from 0 to 28 degrees. If you take the maximum angle, probably is the one that has been grown parallel to the instantaneous stretching axis. So you can use this this angle to find this angle delta between x and the instantaneous stretching axis. Mm. Okay. So there are several variations of this method, but okay, take in mind that we can use quartz axis in different ways to characterize the vorticity. Another interesting, quite more simple method is the use of a rigid Porphyro You can see in this picture uh, transgression with left sense of movement, compression perpendicular to the foliation. You have a stable apophysis here, a rotating apophysis here with an angle alpha. And you can see that some porphyrocluster rotate continuously, developing delta type tails. Some other rotate less and develop the sigma type tails or mantles. And you can see also the famous back rotated porphyroclast because they are rotating in this direction to the right, but they develop the tails according to the shear direction. So the tails are attached on the long side of the crystal. But in this way, I can use the distribution of porphyroclast to detect the amount of vorticity. We use this kind of graph. This is the angle of orientation of the long axis of the clast. On the horizontal line, you have the aspect ratio of the porphyroclast. It is just not the major axis divided minor axis, but it is the axial ratio elevated to 2 minus 1 divided r to 2 plus 1, just a little bit difference. But it is very nice because this is the equation that give you directly the vorticity. So more or less you put all your clast in this graph, means that you have this aspect ratio zero point 0.4, the orientation 6 degrees. You have this spot, this dot, then this one, you plot every one. You can find two kind of distribution. The red one are classes that rotate continuously. If you give a look, they have a very low aspect ratio. They are rounded, more or less. In this part, the yellow class are the class with an higher aspect ratio, so they are more elongated and became more stable and parallelized to the shear plane. And these two distribution are separated by a line, by a cutoff point. You can check this cutoff point. If it is 0.6, this is directly the vorticity in this kind of graph. So 0.6 means that the deformation is made by prevailing pure shear. Some people uses also the tails, so the red one are more or less delta porphyroclast. The yellow one are sigma porphyroclast. Okay, if you are so much tails, you can use, but anyway, you can plot this also the axial ratio and the orientation without taking in consideration the sigma or delta porphyroclast. So you just put all the measurement, the graph, and try to find the distinction, the cutoff point in between the classes that rotate continuously and show orientation up to 90, minus 90, from the ones that are concentrated along the shear plane. And this line as a line of the flow, the theoretical line calculated for the flow of each aspect ratio. So you can have also a graph like this, much more simple. You can plot the orientation of a long axis and the axial ratio. So you put all the point here, and then you can try to find the cutoff line here. But usually there is not only one line, but a zone of uncertainty. So you can put a lower and an upper uh, cutoff line. So you have a range of vorticity, maybe 0.73, 0.78. Okay, but it is exactly the same. So for this method, you need to have a rock with a deformed porphyroclast, maybe some sigma tails and so on, but I don't take care of this. This is a myelonitic foliation. You can have the long axis, the short axis, and the orientation of the long axis with respect to the foliation. So you have the axial ratio and the orientation of each porphyroclast. These are just enough parameters to build up this graph. Okay, if you calculate the aspect ratio, that is beta, I don't remember. Ah, minus -1. And this is also the vorticity value. So we can use this kind of graph. Okay. So it is much more easy to plot on this kind of graph. So these are more or less an overview of the main methods to calculate vorticity. For the rigid porphyroclast method, there are some problems, some prerequisites that you need to know before apply this method. The matrix behaves as a Newtonian linear viscous fluid, so should be simple deformation, Newtonian, not with exponent, and we will not control this, we assume. The class should be perfectly bonded to the matrix, so they're connected to the matrix and rotate, not disconnected or separated from the matrix. The class should be perfectly rigid, so means you have to rotate this one with not a internal deformation. So if you use a class for strain, means they are deformed, you cannot use for vorticity the same class. Okay, this is very important because some people make a lot of confusion with this. The metric strain should be high. The much higher strain has a much better results. And you have also enough population of a class with axial ratio larger than 3 and 4. Because if you have not enough class like this, you can see in this graph, okay, also in this one, you need to separate the continuously rotated cluster from the stable cluster, but here you can have a large number of clusters, not only one or two, because should be very big error moving with this. So you should have a rounded cluster and elongated cluster with axial ratio 3, 4, 5. So you have two population, well-defined population that you can separate by the cutoff line in the graph. And there is also another problem because when you have uh, when you cut the section, you can cut the rocks in this way. So this cluster is cut in the central part, and you can see the maximum axial ratio. This one is cut just on the border, so you have a minimum axial ratio. So you have also some problem of the cutting effect. So Tikhoff and Fossen established an error of the vorticity, more or less 0.1 error, the vorticity. So means that 0, 1 and 0, 2 are more or less the same. But in a paper with Jacopini and some colleagues, we calculated the cutting effect and the several other effects. And to be safe, to be sure, usually the error could be close to 0.02 maximum. So if you have vorticity 0.3 and 0.4, you cannot use to make some bigger reasoning because they are more or less the same number. So you cannot separate these, I mean, much more pure shear, much simple shear. They are the same. So they give an idea of the formation. So if the difference are zero point 0.3, 0.4, 0.5, okay. And due to this limitation, the best thing to do is to apply as many methods as possible on a given sample using high quality data. So don't use only C prime or Porphyrioclast. Try to use all what you have or what you can and compare the result. In this way, uh, you can build up a little bit better data. Okay, just some natural example from Greece. Uh, there are some paper by Xipolias worked on the strain I show you 2 days before, and also he calculated the vorticity approaching in a tectonic unit, approaching the thrust zone. In red, you have the axial ratio and beta method by quartz sheet fabric axis. Uh, this oblique grain shape uses the quartz C-axis fabric, and in yellow, the axial ratio of strain and delta method. So with different method, this the rigid Porphyrioclast method, the blue used in the uh, Mount Everest or at the scale of Orogen. So you can see, for example, in this tectonic unit, you have simple shear predominating the upper part, and pure shear dominated in the central part of the unit. On the unit, then simple shear increased at the thrust at the base, thrust at the base of this unit in Greece, and the same more or less happen in the Himalaya. These are quite old. There are much more data now, but you have something between a simple shear, pure shear in the central thrust, then pure shear increases in the central part of the greater Magellan sequence. Then you have a very large amount of simple shear approaching the South Tibetan detachment using uh, different methods. This just data from Mount Everest area, a little bit similar to this, but not so much. This is the Raft River Mountains in USA. There is extensional shear zone and vorticity changing in a strange way going to the lower part. So you can use also at the regional scale. Of course, when you go through the grid Malan sequence, it's a problem because you have different metamorphic conditions, so the data are not so well comparable. And when you use C-axis fabric of quartz, you have to remember that the quartz could be very easily deformed, so it cannot record all the history of deformation, but only the latest stage. So these are the main limitation. So for this, I I stop you to fill with information and the strange formulas. Thanks. But if you like, there is an exercise, but I can show you simply what to do because uh, just you can estimate the strain. This sample, you know, is made by a rigid porphyroclast rotating during deformation. These rocks are characterized by pure shear, simple shear, and of course, I have not the value for this one because I forgot in Italy. But this is an exercise from Paris Xipolias that put the short axis, long axis, and the angle of the porphyroclast, and just and he also build up Excel program, Excel file at this one. Okay. So I can put here the short axis, long axis, and the angle, and the program, Excel program, calculate the ratio and the step factor. So, for example, this is the top 68, angle 36, maybe the second 33, 46, 70. And if you give a look to this graph, is plotting the point on this graph. So someone wanted to put the number inside just to give the distribution. Some voluntary people. I give you money if you come here. No, just try to what happened and how to decide the cutoff point. No one? Yes. Yeah, yeah. So, okay. 86, 101. Okay, go directly here. 35.
knowledge, stronger connections, and dreams ready to the flight. As this remarkable journey of learning comes to a close, may we carry forward the inspiration, curiosity, and the passion that Gyan has ignited within us. So, together, we have grown, explored, and discovered, and the future now awaits for our contributions. So, today, now, I would like to invite anyone who is interested to come forward and give their feedback. So, please feel free to come forward. Anybody?
Hello, good evening, everyone. Myself, Dr. Pravesh Sharma, and I feel truly grateful to be the part of this course. And I want to thank Rodolfo sir for providing an insight into what really lies in the depth of structural geology and metamorphism. And obviously, I'll try to introduce few concepts in my future teaching assignments and research. And I thank Mahesh Thakur sir for providing an insight into neotectonics, how quaternary geology is a key concept for your research. And yes, the whole course was well structured, and I really appreciate it. And I appreciate GIAN coordinator sir for this. And thank you so much.
Thank you so much for your very wonderful words, sir. Anyone? Anyone out of you want to come forward, please? Anyone? Okay, then let's move forward. Okay.
Good evening to everyone present here. I am Shifali Chip from University of Jammu. So, firstly, I would like to congratulate the organizers, Professor Gurjaspreet Singh and Dr. Mahesh Thakur, for organizing this wonderful GIAN course 2025. So, I would like to share and also acknowledge these organizers for organizing this course, because as a structural as well as a geotechnical engineer, this course has contributed immensely to my academic growth. For example, if we take an example, for example, as a structural geologist, we have to do strain analysis and know how to take samples for strain analysis and how to analyze the thin sections. And I feel fortunate to have learned from Professor Rodolfo Kerosi, a well known structural geologist, because I have known much about the structural aspects of these rocks from him. And I personally thank him for sharing his expertise in structural geology with such patience and clarity. So, from this course, I have learned how to do a strain analysis for the samples, how to analyze the thin sections, and also all the structural aspects which he has shown here in this course. On the other hand, Dr. Mahesh Thakur, being a geotechnical engineer, has beautifully explained all the geotechnical aspects of the tectonostratigraphic units. So I would like to thank him as well for sharing his thoughts on the structural geology aspects. So I think this course would be fruitful for me to come all the way from Jammu to here, Punjab University, and learned this much of experience from well-known and geoscientists of the world. So, thank you to everyone for making this course a memorable and also a valuable course. Okay, thank you. Thank you very much.
Thank you so much, ma'am. So, with this heartfelt gratitude, now I would like to invite Professor Gurjasprit Singh to kindly come forward and present a token of appreciation to our guest, Professor Rodolfo Crossai, and to our course coordinator, Dr. Mahesh Thakur. Now, I would like to call our local coordinator, Professor Gurjasprit Singh, for the word of thanks.
A very good afternoon to all of you. As we conclude this 5-day workshop on the growth and collapse of Orogens and the aggregation of deep-seated rocks in the Himalayas. It is a good moment to look back at the meaningful discussion, learning, and interaction you have shared over the past few days. First and foremost, I would like to express my heartfelt gratitude to the Ministry of Education, Dr. Anil Kumar, National Coordinator of GIAN, our esteemed Vice Chancellor, Professor Renu Vig, Professor Yojana Rawat, DUI, and Professor Meenakshi Goyal, RDC, for their invaluable support in facilitating this program. I would like to sincerely thank Professor Rodolfo Pels for joining us and for sharing his valuable knowledge and insights. My heartfelt appreciation also goes to our course coordinator, Dr. Mahesh Thakur from the Department of Geology, Punjab University, Chandigarh, for his constant support, guidance, and dedicated efforts in making this workshop successful. I'm also grateful to entire organizing team, especially Manraj, Vineet, Mithun, Shwani, Pallavi, and Anshu for their throughout planning and hard work, which ensured that the workshop went smoothly from start to finish. Finally, I extend my thanks to all the participants for their active involvement and keen interest. I hope the experience has been informative and helpful, and that the knowledge gained here will support your future academic and research work. Thank you once again, and I wish you all continued success in your respective field. Thank you.
Thank you so much, sir, for your encouraging words and constant support throughout this program. At this moment, I would like to humbly request our esteemed guest, a local GIAN coordinator and course coordinator, to come forward and honor our students with certificates. Now, I'll be calling you one by one by your names, right? So, Shubham Chaudhary, Dr. Pravesh Kumar, ज्ञान वाला पोस्टर लगाना है मुझे ले आओ नीचे से सुमित सिंह ओके मानिक शिफाली चंदर ओके शिफाली ठाकुर प्रीति ठाकुर प्रीति ठाकुर मनीष कुमार है मनीष कुमार is he present no तुषार चौहान अशोक कुमार श्रेया शर्मा सलोनी is Saloni present over here सोहेल सिंह सोहेल सिंह सौरभ राणा ओके पलक राणा सौरभ राणा सौरभ पलक राणा। अक्षय कुमार। पीयूष शर्मा। पीयूष। आर्य मंगेश। आर्य मंगेश। डॉक्टर सोनू। अनन्या अवस्थी। मालविका भट्ट। मालविका भट्ट। ओके, सरबजीत सिंह। जयप्रकाश। सरबजीत सिंह। जयप्रकाश। जुगराज सिंह। शुभम शुभमन दीप। अजहर। अजहर। ओके, अमनप्रीत कौर। समृति। अनीता शर्मा। राजकिरण। शिफाली। कपिला नेगी। अर्नव मेहता। चालू। शालिनी। अभिषेक। ऑनलाइन, ओके। नीरज। Thank you so much, everyone. Just 5 minutes for a group photo. Just उसे भी करवा रहे हैं, बता रहे हैं।
ऐसा लेना कैसे लेंगे और कुछ चेयर के ऊपर चल जाएंगे तो आई मिलो जो नहीं है मैं कैसे लेंगे
Please come forward for the group photo, guys.